And I think we can start with the first speaker, who is Angelica Tarpanelli from IRPCNR, she's going to talk about satellite products supporting the understanding of the interaction between inland waters and the coastal zone during extreme events, the case study of the Po River drought. Please.
Thank you. Good morning. Good morning, everyone. So this study was born during the Hydrocoastal project because it was a case study on the project that was focused on the interaction between inland water and coastal area. And so we, because Hydrocoastal is a project in which we managed altimetry data, we try to see if altimetry is able to see this interaction, because so far the literature is full of analysis about the sea surface salinity, sea surface temperature, wind, mainly focus on the optical images, but there are no studies that use altimetry. So our purpose is to try to see if we are able to catch something. So we analyzed three objectives. The first one is to evaluate the capability of the satellite to monitor extreme events. So first, we focus on the inland water. Then the capability to monitor the salt wedge intrusion in the downstream section of the river by satellite. So during the drought, there is the possibility that the sea enter into the river. And the third objective is the evaluation of the effect of the river over the coastal area. So the study area is the Po, and the Po in last summer experienced this big drought, and with a lot of consequences for agriculture, for the local population, and the situation was exacerbated by the salt water intrusion into the river, which destroyed crops and with a lot of problems also for irrigation. This figure is an image of the Po during the normal regime, and this is during the last summer. So you can see a lot of, thank you, a lot of sandbars over all the river. But the river, the Po, is also an environment in which a lot of floods occurred. And in 2019, we have these big floods that went to the floodplains and invading farmland and countryside. So again, this photo shows how the normal river can be different during flood. So we focus on this part, the downstream side of the river. These are all the ground stations that we have, and we focus just on these 7, just to analyze the part. And on the coastal area, we analyzed these 50 kilometers from the coast. About the datasets, the ground data are provided by the agency, the regional agency for river discharge, and the interregional agency for the Po River. And for the satellite data, inland water was, we used the altimetry from several satellite missions: Cryosat-2, Sentinel-3, Jason-3, Sentinel-6, ICESat-2, and SARAL. And Karina Nielsen elaborated all this mission in a multi-mission approach. So what we will see is the one single time series that is the integration of all these satellites, because in this way we improve the resolution and we reach 4 days of temporal resolution. For the coastal zone, we use the product of the altimetry coming from Cryosat-2 and Sentinel-3 that are the products developed during Hydrocoastal project. So, to answer to the first question about the inland water and the capability of satellite to reproduce extreme event, here you can see for all the 7 stations that we analyzed, the temporal series coming from the altimetry, just satellite data. And you can see a lot of flood events, especially the one in 2019, and also the drought in 2022. So each time series has this a drop during the summer. But in Piacenza, that is the first one, the upstream, in the upstream part, we have several different behavior. We have this drop, it is not so highlighted like this one. And again, we have a double peak instead of 3 peaks of the rest of the station. So we ask why, and if we look at the longitudinal profile, we know that there is a disconnection between the river, into the river, between Piacenza and Cremona. So this different behavior is due to the fact that the river is not connected, and so also the flood is not moving along the river. These are other satellites that we took from Cryotempo project, in which you can see that it is able also the satellite is able to reproduce the slope quite well. The black line is ISAT2. The green points are CryoSat2. The 2 differences are because they are analyzed in different way, but just to show you that the satellite is able also to reproduce all the part in the longitudinal profile. About to answer to the first question, here I plot the comparison between satellite and ground data for the downstream section Ponte Lagoscuro, Polesella and Cavanella. Ponte Lagoscuro is around 90 kilometers from the mouth. Polesella is around 60 and Cavanella 37. So, and you can see that in Ponte Lagoscuro, the comparison is quite good with good performances. When we go downstream, we have more difficulty to estimate the peaks or the drought, and mainly because I think, but we have to investigate more with Karina, that the multi-mission approach could fail because it doesn't have a long path and many satellites track to identify the good in a good way the river, but also the interaction probably of the coastal area can give some disturb. So here you can see all the floods and again the drought. So focus on these floods and this drought. I want to show you this interesting, in my opinion, image. So here there is the ground data. So for these 3 stations during the flood events and during the drought. Here I put also Pila. Pila is a station practically into the sea, very, very in the mouth of the river. And focus on this window. I selected the minimum and the maximum range for all the path. So you can imagine this line should be more or less this point. No, maybe this point. And this line could be this point. So actually, if we see the longitudinal profile of the river and the minimum and maximum range, we can observe these big differences between floods and drought. And this is quite a good result. So probably the satellite, we can say that the satellite can see the extreme events. The difference is in the water level is around 10 meters. So there is a big excursion and the satellite is able to see it. And so the take-home message to answer to the first question, the multi-mission satellite altimetry is able to well reproduce the groundwater level, and the extreme events are reproduced as well. Of course, there are some margin of improvement, especially in the downstream area. For the second answer, I use the same plot, but here just to, I want to I want to show you this behavior, because this is the ground data, and you can see these are the more downstream section, And this is Ponte Lago Scuro, that is around 100 kilometers from the mount. And this small variation is due to the tide of the sea. So the tide is has more effect in the downstream, but it is able to move until the Ponte Lago Scuro. Of course, this is not could be not reasonable. So probably this small tide is more the energy of the sea to the river more than the water of the sea to the river. But if we look at the slope, this is the slope during the floods, and this is the slope during the drought. And you can see the horizontal line, the horizontal slope of the two extreme events is different. So it means that here we can suppose that the water of the sea reach at least 70 kilometers and then increase again with the slope of the river. So of course, this is our first analysis, and we can put more energy on this message. But we can observe two things. The first is that the variation of the tide cannot be seen from the satellite, of course, because the frequency of the satellite is raw. But the slope of the longitudinal profile can give us some indications on the effect of the sea level and hence the salt wedge intrusion. More analyses are necessary, of course. For the third objective, so the analysis of the plume into the coastal area, we analyzed several passages of Cryosat-2, like the one in blue here, and 4 tracks of Sentinel-3. And the analysis was done in two ways. The first, considering just the flood and the drought into the sea level anomaly of the altimetry. So over these tracks of Sentinel-3. The other analysis was focused on analyze the similarities between optical features and altimetry sea level anomalies. And we focus just over the flood events. So about the first analysis, this plot is quite interesting because we saw here in orange and red until here, these 4 are 4 floods events. So we are here in this track close to the mouth of the river. The river flows like here. And we observed that there are, in 2019, 2 big effects of the river. So the water of the sea increased. And during the drought, we have again another effect. So the level of the sea decreased. And this difference is about 40 centimeters. So the river has an impact on the sea level anomaly. And similarly, for this other track is far away from the mount, but we can observe these big differences between flood events and drought events. The second analysis focus on the correlation between, if exists a correlation between Sentinel-2 images and actually analyzing the plume of these images with the sea level anomalies. And these are the image in visible band. But if we play a little bit with the band, it is more easy to see the plume over these 4 events. And here you can see the track of satellite altimetry, and the color show the correlation between the water, the sea level anomaly, and the band that we analyzed in Sentinel-2. And you can observe that yellow, that is almost high correlation, it is often close to the plume. But there are also some other effects far away. This is not a very robust analysis because The image of satellite does not correspond to the time in which we have altimetry data. So it is better to have at least more image to analyze exactly the consistency in time of the two satellites. But show us that there is some correspondence, and so it will be an added value to analyze also the altimetry in this on this aspect. So the take-home message here is that these preliminary results underline that the river plume has an impact on the coastal area. However, more analysis need to be carried out to take into account other factors like the currents, the coastline bathymetry geometry, and wind stress, earth rotation, and so on. So the recommendation in this case is that with a multi-mission satellite altimetry, we are able to follow the evolution of the water level into the inland water. And so we are able to estimate extreme events. So it is highly recommended to have a multi-mission approach. A second point is to ensuring the continuity of the product from river to the sea. So we need to analyze with the same retrackers, with the same correction, with the same methodology, the two environment. We need also to develop an improved mean sea surface to be used in the coastal zone, to be coherent with the geoid and at the land sea boundary. And of course, because we have this problem in timing, it is maybe it could be useful to have some commercial satellite imagery to have more data to compare with during the passage of the altimetry, for example. And one interesting thing is to use some ocean current measurements available already in the North Adriatic Sea to better characterize the ocean circulation and its variability, especially during floods and drought events. So I think we have many things that we can do. And so these are just a preliminary study. And if you have comment to add some good suggestion, you are welcome. Thank you very much.
Thank you, Angelica. We have time for a question.
I have a quick comment. Thanks for the recommendation. Thanks for this very nice presentation, all these use cases that you looked at. What about the follow-on of hydrocoastal? For instance, what would you need to unite the work that hydrocoastal has done on the inland, the hinterland part, and the coastal part? Like what's going on in the estuary, and what about recommending to put all that data into a model that would explain, or let's say a model what is going on in the interaction between the coastal zone and the river. So the follow-on of hydrocoastal, what is it?
Yeah, I think hydrocoastal was a good project, maybe too long. but there are some missing stuff. All the modeling of the coastal area is missing. If we want to, and we have some modeler in the inland water, but we don't have modeler in the coastal area. If we want to analyze the interaction, I think the model is important. And so maybe should be good to have these experts on this on this aspect, and also people that work because there are already people that work on the interaction between inland water and coastal area, but not with altimetry, with other sensors, and so probably it should be an added value to have this expertise. So altimetry is one of the site, and this was not investigated before, but I think we have to take care of the heritage of all this stuff.
So if you want to, if you want to update your slides, adding what we should add to hydrocoastal
Okay.
in the future that would drive us in the right direction.
Okay.
And then the yellow tracks on your plot are Sentinel 3B, not 3A, but that's just a
Ah, sorry.
detail that you can adjust. Thank you very much.
Thank you.
I would also have a quick question. Could you specify the amount of water of discharge is necessary to be able to see it in the ocean? Is there some threshold also, what you say, to see it in the
You know,
droplet?
The main objective that I had was to investigate the volume.
Yeah.
And in a very raw way, if you take the area, if you take the height, you can have a value of the volume, you know, but we need the time. So how much time do you need to accumulate all this volume? So if we are able to do this, we are able to see all the volume entering into the ocean at global level. So just analyzing small pieces. So it is a very big objective, but it would be nice to see. But I think I don't know very much about the coastal area, so we have to work with other people that know this stuff, and because it is not a problem it is not a static water.
Yeah.
So we need people that understand everything, the current and the wind and the tide, and so it is not easy. But it could be nice to have this information. Yes.
Okay. Thank you very much.
Thank you.
So the next talk will be given by Caterina Cicilio from Atlantic CoLab, and the title of the presentation is the EOIC Coastal Total Water Level Product Development, Validation and Application.
Hello. Yeah, can I do this?
It works.
So good morning. I'm Catarina Cecilio from Collab Plus Atlantic, and I will present the work entitled the EOHC Coastal Total Water Level Product Development, Validation and Application. So the presentation will follow these steps. I will say a little bit of the context, then I will go through the development, the validation, and I will show 2 examples of application. Oh, sorry. So this work is part of the project EOHC, that means Earth Observation at Sea Level Extreme Events, and the project aims to provide the advanced reconstruction of the relevant process during the extreme sea level events and their associated coastal hazards, using the recent advances in EO data. So what is this extreme sea level event? They happen, what is and when they happen? They are like different drivers from ocean and atmosphere combined, and they happen when we have this process rising the level at the coast that exceeds the natural or artificial defenses causing damage and coastal hazards. And we're gonna call this sea level at the coast as a total water level. So the goal here is to provide a product that can reconstruct this total water level. Here is the website of the project. You can go there and check. There is a lot of work going on. And those are all our partners. And it's founded, this project is founded by ESA. So how are we gonna do it? We're gonna combine all the process that is happening at the same time, so that can rise the level of the coast. However, we will not use the river discharge as it was said in the before presentation. So we're gonna use just the effects of the waves, how can I show it here? how can I use this? Oh, it's okay. So we're gonna use just the effect of the waves, that is the R, the storm surge, that's here, the SS, the astronomical tide, and the sea level anomaly, all combined using the linear summation downscaling empirical modeling approach. Just to notice that this methodology consists in the co-occurrence of all those processes. However, it not account the nonlinear iteration of that. Here is the workflow to develop the product. You just need, like, it's really simple. You just need to select a position and then run all these scripts that will go and get all the data, download it, pre-process with an intermediate output of time series for sea level anomaly, wave run up, astronomical tide, and storm surge. Then we're going to put all together to provide one time series of the total water level with hourly temporal resolution. Here's the data set used, like the one that gave us, like, that makes this work different from the others is the use of the extract L2P product, that it's a long track multi-mission data. So we had to use all those tracks to compute just one time series. And I will talk a little bit more about each of them. So first of all was this sea level anomaly time series. As we wanted to combine all the tracks, the first thing we did was analyze each track time series to see how was it. And in this first approach, we saw that the satellites, the HY2A satellite, the time series was without a small bias there. So at that point, we decided to just drop these tracks. Also because we had different tracks at the same period, so we could use the other ones. And also we reported to the developers that then confirmed the bias, and then they corrected and developed a new version, that is the version 2.2.1. So if you're gonna use now, you can use with this satellite. So, but when we did, we dropped it. So our results is without this. Then we had to decide a point to extract this time series. This point should be as close as possible to the coast, as we want to see the sea level extreme at the coast. However, we should respect the limitation of all our data sets. So we decided to put the points like in deep water, as you can see the black dot in that first figure there. And then we tested different thresholds to find the closest point in each track, the closest point in each track to these main points. So at the end, we had this time series with all the different tracks, what gave us temporal resolution from 2 to 5 days. In this case for Portugal. However, in some places we could find even better temporal resolution, and at some points a bit worse. But it was really good result. For the run-up, that is the effect of the waves in the coast. We had to use the wave height and also the beach inclination, that is the slope with the letter bed there. So for it, we used the waves reanalysis, that's global wave reanalysis. And we also, as it's a quite new project, we are using in the coast, we evaluate validation for this data. So we evaluate the waves and also the sea level anomaly. So we did a validation with in situ data, and also we did a benchmark here with the sea level anomaly with the reference data normally used for this kind of products. back here in the wave run-up, we used the Stockton 2006 parameterization, and all this work were done in Python, and we used a toolbox named PyWave run-up. For the astronomical tide, we used the FIS 2014 tide model, also with a Python toolbox, and the final result of tide is the oceanic tide plus the losing tide. For the storm surge component, we used the dynamic atmospheric correction that is based on the MOG2D model, and also the inverted barometer correction. And you can see here in this figure all the components together. That's gonna be the total water level at the coast. And here is our final product. You can see all the different time series, and then in blue you're gonna see the total water level. In this figure, you can play and see like 1 month. It's gonna appear here, like here is 1 month, and then you can see all the time series and see which component has more effect at that time. And the final product has that we reconstruct has goes from 1994 to 2021 in our time resolution. So for the validation, we choose 5 use cases to validate the new data. We try to get like the most different environments. So we choose one oceanic island, open oceans, open coasts, and also enclosed seas. But also we had to find places where we could have in situ data to compare. For the validation of the extract, we used tide gauge data from the permanent service for mean sea level. And also we compare with the DUAX product, also from delivered by Aviso. And for the validation of the waivers, we used in-situ data from buoys. Here is the results of the comparison between the extract, our sea level time series from extract and the in-situ data. We can see that the results were so good. With the correlation going from 0.94 to 0.76. So we had the best results for Marshall Island, that's an oceanic island. So it's much easier for the satellite to measure. And also the worst was in that coast, that's the enclosed sea. The RMSE were below 0.07 meters, but also we had the lowest one with 3 centimeters. That is quite good. So overall, we find that in open ocean environments show us the lowest, so the better results when compared with the same enclosed sea. So the benchmark was done with this product from Aviso, that is the reference one, and this preliminary results show that the DUAX, that is a graded product, shows an overestimation of the sea level anomaly, and the higher RMSE was in Dutch coast also. For the validation of the waves parameters, here I'm going to show you the comparison with the height, the wave height. However, we did it also with the period. The results here, what we can see, like that's most evident, is that in the extreme values there is a underestimation of the values in the extreme. So this is was already reported by literature. So, and it's one of the next steps is to try to correct these to get better results for the extremes as we want to see it. And here just showing an application of our project. Here is during the storm Hercules, where we have a lot of damage here in Portugal. And you can see that this part here, the total water level is exceeding the wall level. So there you can see the seawall elevation, and here the dot line is the same position, and you can see that the water goes over. And these results indicate the capacity of this new project in predicted. Another work that has been done in the project is they are using the total water level to calculate the return period and also to predict extreme scenario, future extreme scenarios. This work has been done by one of our partners in University of Bologna, Italy. And yeah. And just to finalize, we thought that the X-track and long-track data improved our estimation of the total water level project. Also, we saw that the semi-enclosed and open ocean needs to be more investigated. And also, as a next step, we want to implement this pipeline in a production way, so it can be replicable to different parts of the globe. One recommendation is to improve coastal measures. That's crucial for this work, and also integrate the in-situ data and EO. There is also a manuscript in preparation that will be available soon. That's it. Thank you.
Very much. I think there's a question. Yeah, please.
Yes, impressive work, but I'm not an expert, so for what it was. Quick question, though. How critical is the DAC estimation, and did you find any limitation, especially during extreme events? Because I think that probably the models are not quite good to predict the appropriate pressure, especially during storms. So I don't know if it's something that you looked at, especially comparing to in situ measurements. And
no, we didn't. But yeah, it's a good question. We should look for it.
with Lorraine Carrère at CLS, I think that she would, Lorraine Carrère at CLS, she would have some good idea on that. But
yeah. Maybe they know better than me.
It would be interesting. Thank you again.
Thank you.
Yeah, sorry, so something I didn't really get. You have a slide with all the contributions.
Which one?
I don't remember the number, but a few before.
This?
Nope. This, yeah, let's say this one.
Okay.
So SLA measured by altimetry sees the tides. So it's I suppose it's corrected in the first one, but I don't really get why the tide has been removed from the observations and then added again, maybe with different models. So you might be introducing some errors. Unless it's exactly the same model, then I don't really see the point.
I know what you mean.
Or it's just to see the different contributions, maybe.
Yes, but also because we need to add the wave run up. That's not in the mean level, sea level, because you're saying that the sea level anomaly is the storm surge and the astronomical tide. Remove it. Yeah, no,
No, just tell. So 80 is already in SLA, should be. It has been.
No, it's removed.
Yeah, it's been removed and added again.
Yeah.
Okay. Okay.
Yeah.
Okay, so it's the same thing. No, but at least it allows you to see the contributions of each thing, I guess. But I mean, it's already included in the altimetry.
Yes, I know what you mean. Yes, just because we need to have all those.
The contribution.
Yeah, separated.
Okay.
Any other question?
Well, okay, so thank you again. We move on to the next speaker. Is Jean-Christophe Boisson, who I think also has another presentation in the other session later today. So
it's not me in the other.
it's like
presentation.
20. So, let's hurry up. Combining large-scale in situ network and satellite data towards digital twins of river, please.
It's a PDF.
It's a PDF.
Yes. Okay.
Okay.
Just two minutes. Perfect. Okay, so I'm Jean-Christophe Poisson from Vortex.io, and just a bit information on this presentation. So I changed a bit the content of this presentation to focus more on in-situ data because for digital twins, of course, but because I heard a lot of things about in-situ data in the beginning of the meeting, and I wanted to put a focus on this topic. I think maybe it's one of the recommendations for the meeting to have maybe a little more presentation and session about combining in-situ and satellite or using in-situ data properly in the different application that we need. So concerning digital twin, so first first reminder, an easy reminder. So a digital twin, what is it? It is a virtual representation of real-world entities and processes synchronized at a specific frequency and fidelity. It helps a lot to do many things, and we see very interesting results since the beginning of the conference for concerning digital twin. So we need different things to do a digital twin. And if we look at the Gartner analytic continuum, we saw that the digital twin is at the totally end. So at the beginning, we have the descriptive analytics, so real-time data. We have data that descripting the systems, measuring it, etc., etc. So this is what happened. We can measure it. Then we go to why did it happen, to analyze with all this in-situ data, satellite data, and so on, to model, to understand what is going on. Then once we understand, we want to predict what will be the future. So it's predictive analysis using the simulation, the modeling, all the data we have. And then finally, we will build the digital twin, which is prescriptive analysis. So we can run different scenarios in order to see what is going on in different scenario, depending on what happened, if there is more precipitation, less precipitation, and so on. So we can force the system and use different things. So following this slide from ECMWF, concerning the digital twin, the replica of Earth's destiny, what we need and what the beginning of the digital twin is to combine satellite, in situ, and modeling. This is really important, and this is the basis of the very digital twin. So observations and simulations. So concerning satellite data, I think I've seen plenty of presentation this Hydrospace meeting, and we saw that there is plenty of missions. There is more and more missions that are launched, many parameters that are observed. So I think I've seen extremely interesting results from this. So I think we have a lot of parameters from satellite data, a lot of vision of the different components of the Earth and of the hydro. So it's very interesting. Concerning modeling, I will not speak a lot about modeling because I'm definitely not an expert in this part, but I saw also plenty of models, plenty of way to use the data, to combine it, to simulate, to understand, There is AI also advanced that put a lot of things into modelings and improve the modeling. So I think it's not a problem. But I heard a lot about in situ data, and I think in almost each presentation we use in situ data. But we also this graph also, the number of in situ data that is decreasing with time. And I think this is a very big problem, because we know that in situ data is used in many applications for digital twins, of course, but not only for validate the data, for calibrate models, and so on. And we saw that the number of in situ data is decreasing with time since the 90s. And so this is a real problem. And how can we tackle this information? Most of the time I heard that satellite data can mitigate this and replace in situ data, but we have also interesting discussion in the beginning of the conference that we have difficulties to reproduce very fine events because of the sampling of satellite, because satellite is not necessarily here where it is needed, etc., etc. So we definitely need this in situ data, and we need the complementarity between satellites and in situ data. So what is the main reason of the decreasing number of in situ data? Most of the time is because the current in situ solution are not deployable at large scale. It's not maintainable. And we saw that with in situ measurements on rivers, only 5% of the world's rivers are monitored with in situ data. Only 5%. It's really slow. Really low. Of course, in Europe, in the US, it's better than that. It's close to 20, 25. But in the world scale, it's very difficult. And because in situ data are very, it costs a lot to buy a sensor. It costs a lot to install a sensor. It costs a lot to maintain a sensor. And the maintenance is the key of in situ data. So this is a real problem. And this is what I wanted to talk to you today, is because we are working on new solution. There is some hope for in situ data. So at Vortex, we develop an innovative in situ systems that has been developed as a satellite, but that doesn't fly. We make the assumption, and we saw that when we launch a satellite, if there is an issue on the platform, we can manage everything remotely, and we do not send an astronaut to repair, to fix the satellite. So we design an in situ sensor that is built and designed as a satellite. So we can manage everything remotely. We can have the data remotely, but we can also have a complete remote supervision and digital maintenance. We can send updates, etc. And we designed this station as a platform where we can put different sensors. This is really important because I think there is many parameters that must be provided to the users for digital twins, for modeling, for CalVal, for calibrating the models, and so on. So the station has been designed to be very easy to install. In 1 hour, we can install a station. It's not in contact in water. It's based on remote sensing techniques as a satellite. And it's autonomous in terms of power supply, with solar panel as a satellite, fully connected, and so on. So this solution can be very interesting for many applications. On board on this on the current version, we have a LiDAR with measure the water level with a centimeter level accuracy. We have a 8 megapixel camera with IR capability in order to have night vision, but also to have multispectral capabilities. So we take pictures each time we make a measurement, we combine the water level measurement, and we take pictures, and we take videos also from the rivers. We have on board an accelerometer, which controls the pointing of the station to be sure that the measurement is okay, such as a satellite. We have thermal sensors in order to measure the water surface temperature for water quality information. And we have also a precise GNSS receiver on board measuring in permanent the precise position of the station, which is very interesting. But also we can derive many parameters from the GNSS measurements. So this is some example, very simple of the water level measurement that we can have, the comparison between different water level on the same river with different station. The images of water courses that we take, and the water surface velocity algorithm that we produce and that we process the video in order to provide this water surface velocity. We have also developed something that I think it is very interesting for users, is the river cross-section measurements for river discharge measurement, of course. That can be very interesting also to combine with satellites in order to compute the river discharge. So we just use the camera on board. We use a machine learning model in order to build a water mask. And then we associate each water mask at the water level that we measure. And then with time, with the evolution of the rivers with time, we can draw the cross section and measure the cross section of the river. This is an example on a river in France. So that can be very interesting for you. We have also in situ precipitation measurements, which are very interesting, and I think this is an essential variable also for modeling, for CalVal, and of course for digital twin. So as you said, the local rainfall is a trigger, is a forcing variable of the hydro system. And we developed a solution called Rain GNSS. Bruno Picard told a bit and detailed a bit the system during its presentation yesterday. But the idea is to use GNSS signals that crosses the atmosphere, that has been modified by the atmosphere. And so to use this modification to invert it and to provide precipitation measurements. So this can be very interesting, and we designed the solution with respect to a rain gauge because we wanted the solution to be robust in time, to be easy to maintain. And we all know that a rain gauge, a standard rain gauge, needs a lot of maintenance. You need to go on the field to calibrate, to remove an insect or leaves inside the rain gauge, and it's something difficult. We designed all the solution to be easily to have an easy maintenance and to be able to do everything remotely. So there's no new integration of hardware inside the station. It's very easy, no calibration needed, but there is a lot of work on the algorithm. And the main thing is there is no aging and no maintenance needed because it's a simple GNSS antenna. So really easy. But we are working also on new technology that can be very interesting also. And the new technology of drones and autonomous drones. So drone is a flexible sensor that's very useful for hydrology, I think, to take pictures, to take also measurement of the water level. And we use a lot this solution for calibrating SWOT currently, but also for calibrating Sentinel-3 with the street art project. So I think we demonstrate that it is very useful to have all this measurement of the water level along the drone flights, but also to have pictures of the rivers and to compute also water surface velocity from these videos. So the drones that we are using are not autonomous yet, but we are working on an autonomous solution that can perform regular measurements at specific location, can be deployed at large scale also, that will strongly increase the number of river profile measurement that can be useful. And it is usable in different conditions, flexible condition, also can be deployed during floods. That can be very interesting. And we have a specific presentation on it that will be done tomorrow by Valentin. One thing also we provide with this station, and I think it is something that I heard a lot of needs, is in situ water quality. We speak a lot about quantity, about the hydro cycle, but we need also water quality measurements. And so we try to put also a measurement of water quality on the station. So with water surface temperature. So we have a poster dedicated on this specific topic, but also water turbidity. And having this in situ data can be very useful also for calibrating satellite images, to calibrating water turbidity from satellites, and also to monitor, to have a daily monitoring or continuous monitoring of the temperature and the turbidity of the water. That can be very useful. So what's next? What's next with this system? So as we saw that the number of in situ data is decreasing. But it's not by designing a new system that will increase the number of in situ data. But we design the system to be easily scalable and also to be at low cost. So the idea is to deploy at large scale this system to tackle the problem, the issues that we have with the number of in-situ data that is decreasing. So we submitted a project at Vortex, which is called WILD, the Worldwide Hydrology Large Scale Database. And we have been awarded by the European Innovation Council to deploy at large scale this system and to demonstrate that there is a lot of R&D activities and a lot of things that can be done with a dense network of in-situ data over rivers. So we started this project with two pilot countries, which is France and Croatia, and we will deploy 1,000 sensors in these two countries. And this is just the beginning. We wanted to go further to install more and more in-situ data where it is needed in order to complement and to have the complementarity with satellite. And I think it is very, very interesting and mandatory for all the study I've shown during this conference. So this is my main point, and I come to conclusion. So as we said, in-situ sensors are mandatory for exploiting satellite measurements, for modeling also, for calibrating models, to use also for developing digital twins. So for CalVal of satellite, to bring the continuous monitoring we have, to bring the high sampling, and so on, and many applications. We saw that the number of in-situ data is decreasing with time, mainly because of the sensor maintenance cost and the sensor cost also, because current solutions are not designed to be deployed at large scale. So with this new solution we propose, we think that we can provide a new solution that is low cost, that can be very deployed at large scale, and especially with the WILD project starting in February 2024, the large deployment, and providing multi-parameter for both water quantity and quality. And I think it is very interesting to have this platform and to develop this platform and to bring new in-situ measurements all the time to the community. Some recommendations. So I think one recommendation I would make is to put some efforts to make in-situ data easily accessible, downloadable, and usable. I think we all have made the experience of be interested in some in-situ data in some country, in some region, to go on the website, specific website, finding the provider is difficult. When we have the good provider, finding the in-situ data sometimes is difficult, it's not easy to access. Finding the good format, sometimes it's, if you change of country, the format is totally different, the altitude reference is different. It's not calibrating in the same way, so it's very, very difficult to use in-situ data, and then to download the data and to get the data. So I think there is a lot of efforts on in-situ data that must be made to be wider used and to have an homogeneous format, for example, or homogeneous downloadable and usable data. Do not forget also in-situ water quality data. I heard a lot about reverse discharge, water level, and so on. But I think there is also plenty of database of quality data, which is very difficult to maintain for the different stakeholders. But deploying in-situ water quality data is very important also for calibrating also the models and developing digital twins. One recommendation also is collecting, homogenizing, and disseminating good in-situ data, which ESA called fiducial reference measurement. It is really, really important, and it is mandatory for many studies, many applications to have calibrated in-situ data that we can trust to be used inside the different applications. And ESA launched a very interesting project we called the Street Art Project, which aims to provide this FRM for the validation and the CalVal. But I think this kind of project must be widely deployed for other also topics, not only CalVal, but for different things and on different parameters. So I think it's something that must be encouraged. And finally, sometimes I heard that we use satellite data because in-situ data is not good or because there is hole in in-situ data. So to replace in-situ data, we will use satellite data and so on. And most of the time, or sometimes, I hear that they both they set satellite data against in-situ and etc. And I don't think it's a good way to think. I think they must complement each other and to work together and not it's not a competition between in-situ and satellites. Both are mandatory. It's really useful, and the new application will rise with the combination of the two. So that's my main recommendation, and thank you for.
We have one question.
Hello. I liked a lot your perspective. They are complementing each other. And yesterday also in Madeira case, I tried to show that in a way. I wanted a comment and a question. The comment is that can be also useful for these cases of debris flow when this debris flow clearly enables to have an instrument. So it's another way to put it. In the Madeira case that I showed yesterday, that was clearly the situation. They cannot have instruments because they are destroyed with the next flood. So that's the one comment that supports that. The question was just, you mentioned that there were 3 sensors, infrared sensors. What were the differences between them? I didn't catch it. Maybe you could, and what they are used for.
Yeah, so there is multispectral camera for water quality mainly. There is also a IR camera for the night vision because we have IR projector and we can see the river at night. And we have IR thermal sensors for only water surface temperature. So it's 3 different IR sensors, yes.
Okay.
I would also have 2 quick questions. So the first one is regarding your first comment that the data should be easily accessible. Will the data also be free available for everybody?
That's the main question. It should be. It should be clearly, and we try to do to put the cost as low as possible because to make available the data. But each time we work with a public entity, we make the data available because it has been paid by the public entity, and so it should be disseminated to everyone. But the in-situ data has a cost, even if it is low.
Then I would have also a more technical question regarding your sensors that you are measuring the cross section.
Yes.
Is there a limitation of the river? Because I think you have to be, it must be a smaller river that you can cover the whole river by the sensor? Or?
Yes, exactly. We need to see the both banks. So we have a wide angle camera on board, so with 130 degrees of vision, but there is a limitation because we put most of the time our sensor on bridges or structures. So depending on the height, it's limited. We are able to retrieve this cross section for rivers up to 50 meters with one station for the moment. And if it is wider, we can put different sensors. But
thank you very much.
Thanks. Thank you.
So we are coming to the next presentation, which will be given by Mariette Voigtenhill. Drought monitoring and early warning in Mozambique with satellite and satellite soil moisture data.
Okay. Interesting. Hi everyone. So I'm going to talk a bit about drought monitoring and early warning in Mozambique using satellite soil moisture data. What I'm going to show you today is a combination of many projects that we had at the Technical University of Vienna in collaboration with the University Eduardo Mondlane from Maputo, Mozambique, and also with CNR-IRPI, where we had some projects from the World Bank on drought risk financing using satellite data. So just a quick overview. I think we've all seen this before. So this is an IPCC report figure. And what we can see is that actually in the southern and southeastern parts of Africa, we can see that it's expected to have increasing temperatures during the hottest day, and also that the soil moisture will change and these areas are getting drier. So Mozambique is located here in the southeast next to South Africa, really. And so to look a little bit at the droughts in Mozambique. So I think most of you probably know that a drought is basically developing from a precipitation deficit or high temperatures with increased evaporation to a soil water deficiency and plant water stress. And then we can have, of course, reduced stream flow and reduced inflow into reservoirs, and it can eventually also result into a famine. And what we're seeing here on the bottom is the number of people that were affected by droughts in Mozambique in the last, let's say, 40 years. But if you look here at the occurrences of the drought, we can see that there were a couple of droughts in the 80s and the 90s, but actually from 2000 on, we can see really an increase in the number of droughts, and also that
the droughts have been quite severe or impacted a lot of people in the last 10 years, so to say. And here are the regions where the droughts were occurring. So the drought in 2021 was mainly in the north of Mozambique, but a lot of the droughts, let's say in the 2010s and 2000s, were mainly in the central and the southern part of Mozambique. So in the projects that we have, we work a lot together also with the users. For example, we work together with the World Food Programme, with the Red Cross, also with meteorological agencies, with the disaster risk agencies in Mozambique. And we also had a couple of user workshops to really get information from them, like what is needed in Mozambique for you in terms of drought monitoring capabilities. And the answers that we got from most of them is that they want a near real-time availability, but also very important that future availability of the drought indicators is guaranteed and that it's reliable, validated products. What they really like to see is that we have evaluation with other products. So for example, not only using precipitation, but have a convergence of evidence looking at precipitation temperature, soil moisture, and also vegetation impacts. And also to compare the drought indicators that are existing to the historical impact data, which is a tricky thing to which I'll come back later. And some of the things that they would also like to have, because if they can tell us their requirements, we can basically get a lot of things that they want to have, is forecasts of drought conditions 3 to 6 months in the future. They basically want to know, let's say in September, if in March they are going to have a problem, which is logical, but is also a challenge for us. So yeah, just some of the things that we found out that were that's a bit problematic, or let's say what are the challenges in terms of drought monitoring and using satellite data. This table, I mean, you cannot read it, but it's just to give you an overview of what drought indicators there are available. So this is coming from the WMO drought handbook of drought indicators and indices. So there's really a massive amount of drought indicators that you can choose from. So which one is the one that you're supposed to use, and which one is, for example, useful for the Red Cross or the World Food Programme to use in their monitoring systems. So one of the drought indicators that or types of drought indicators that I want to talk to you about today is using soil moisture data. Soil moisture data can give us some information on, let's say, the agricultural drought conditions. So it gives us a direct indication of soil water deficiencies and is directly related to plant water stress. Whereas, of course, rainfall and temperature are drivers of crop development, but it excludes direct information of evaporation or runoff, for example. And NDVI is an indication of vegetation status, but also doesn't tell us necessarily about the crops, or like the yields, or if there's yield losses. So that's why soil moisture is also a very interesting data set to use for drought monitoring. Then the next step, we have a lot of drought indicators that we can choose from. We also have a lot of soil moisture products from satellites that we can choose from. So which one is the one that you're going to use for doing drought monitoring? So this is a table of, let's say, some of the products that are available. They all have a different temporal coverage. They have a different temporal resolution. The latency is different for all of them. The spatial coverage, like everything is different. And then, of course, you can choose, let's say, the freely available products. But there's also, let's say, the paid products, which is now from Planet, of course, which used to be Wandersat, which has a 100-meter spatial resolution, but is behind the paywall, basically. So what we've been working with in the different projects that we had is that we used, let's say, all the different soil moisture data sets to really see, okay, which one is the best data set to work with in terms of the quality, but also in terms of the latency, the spatial resolution, et cetera, et cetera. So how do we choose our soil moisture data set from satellites as the data set that we're going to use for our drought indicator? So there's a couple of things that we can do. You can always do a classic validation with in situ sensors. And as you can see, this is part of the project that we're now having in Mozambique, that we're installing in situ soil moisture sensors in Mozambique, in the provinces where we're focusing on together with the Red Cross and the World Food Programme to really develop their drought indicators and validate them. So this summer, my PhD student and me were in Mozambique installing soil moisture sensors, which was quite challenging in, let's say, the dry period in Mozambique. And digging holes is not so easy. Yeah, so we have the in situ data, and I mean, we installed them this summer, so at some point we'll have enough data to look at satellite data. There's also the International Soil Moisture Network, but as we can see in those areas where it's actually very interesting and where it's very needed to have drought indicators, there's no reference data from in situ sensors. I mean, it's basically in Australia, the US, and in Europe, we have quite some sensors, but if we're looking at South America, Asia, and also Africa, there's almost no reference data available. So it's very difficult to check the quality of the satellite data set without having this reference data. We can, of course, also use models or do an intercomparison between the different soil moisture data sets. So this is a comparison between ASCAT, surface soil moisture, which is the HumanSat product. Then we have your ERA5 soil moisture. And we have the ESA-CCI passive soil moisture. And we're looking here at trends in the soil moisture. And then the question is, well, what is our true data set? So which data set is representing the trends? So this is also something that's very difficult by intercomparing these different data sets, that what is the true soil moisture trend in these areas. So what we've also been looking at is to do convergence of evidence. So what we're seeing here is, okay, so this first column here is precipitation from chirps. Then we have land surface temperature anomalies. We have surface soil moisture anomalies and NDVI anomalies. Those are from MODIS, and the surface soil moisture anomalies are from ASCAT soil moisture. So we're looking at January until March 2016. Yeah, and we can see, let's say, we can see the deficiencies in the precipitation are also seen in the soil moisture anomalies as well. And also the areas where we have precipitation deficiencies, we can see that the NDVI also shows negative anomalies. So this is a way that we can check, let's say, how a drought is developing, and also if our soil moisture data sets correspond with other data sets. So if we think about, let's say, the soil moisture indicator, drought indicators from soil moisture data sets, there's a couple of approaches that we can use. And some of them are based, or most of them actually are based on anomaly approaches, so deviations from the long-term mean, which means that we do need to have a long-term satellite data set to really calculate reliable anomalies. Yeah, so some of the most used are, for example, the standardized soil moisture index or the soil moisture deficit index, and also the soil moisture anomaly percentage. There's also plant available water approaches, which are based on soil properties, for example, the soil water deficit index, which scales soil moisture between the wilting point and the field capacity, and based on that, it calculates a drought indicator. But let's say another challenge is, and this is something that basically all the stakeholders want to know. So what is then the threshold at which point I need to take action, or when is a drought so severe that we really need to go there? And this is one of the very challenging things, because so this figure is from a literature review, which basically summarizes the common thresholds that were used for the different drought indicators. And if we look at them here, so these are different drought indicators. This is the percentile anomaly, the SMAPI, the Z-scores, and the SPEI as let's say a reference. We can see that if we look at the thresholds and we make the thresholds into extreme, severe, significant, moderate, and mild droughts, we can see large differences between the different drought indicators. So it's very hard to say to someone, well, no, this is now a condition where you really need to go out in the field, or where farmers are going to need assistance. Because even the drought indicators that are all based on the same soil moisture data sets give us completely different drought severity levels. Okay, to also, I told about the challenges that we are having when we're doing drought monitoring, but to also show you some optimism in things that we can do with satellites, remote sensing. So we've been working now also with Sentinel-1 over Mozambique. So this area that you're seeing here, this is Chokwe. This is in the south of Mozambique, close to Maputo. And we've been looking into developing drought indicators based on Sentinel-1. So what we can see here is that we have an extremely high spatial resolution in the soil moisture that we have. And we can see that, so Chokwe was also had very severe drought conditions in 2016, and we can see that we have extremely low soil moisture during this period. And what we've been doing is, because one of the challenges with Sentinel-1 is, if we want to calculate drought indicators, we need to have, let's say, the deviations from the mean or the anomalies at least, but Sentinel-1 only has a time series since 2016-15. So what we've been doing is that we've been combining Sentinel-1 with ASCOT, both our active microwave C-band sensors. So one is a spectrometer, the other is synthetic aperture radar. And we've been combining those to calculate, let's say, anomalies for Sentinel-1. And this is what we're seeing here. So in the black line, we can see the ASCAT seasonality. So this is a 6.25 kilometer spatial resolution data set that goes back until 2007. And then in blue, we can see the Sentinel-1 soil moisture. And in red, we can see, let's say, the soil moisture anomaly percentile index, so the drought indicator. This is for Masinga, also in Mozambique, let's say, also in the southern part of Mozambique. And then what we did, because reference data is not very easy to get, we have been comparing our results now to, let's say, reports from FuseNet, from the World Food Program, etc. And what we're seeing here is that, so let's say in 2019, we've been seeing below average precipitations in October, which is very clearly here that we see a very late start of the season in the soil moisture. Then we had erratic rainfalls in the beginning of the season, let's say in 2020, which we can also see. So the start of season seemed to be okay, a bit delayed, but then also in the middle of the season, we had below average rainfall from November to January, which we see also very clearly here. Then we had an early season drought in 2021. So this is also very clear here that we have a delayed start of the season. And then also in January, February, we had rainfall that was below average in 2022. Which is also very clear. So let's say our Sentinel-1 soil moisture drought indicator does correspond very well to the reports that we have from the World Food Program. If we then look at the spatial, let's say the spatial drought indicator. So on the top, we have our combined Sentinel-1 ASCOT drought indicator. On the second line, it's when using only ASCOT data, and then we have precipitation anomalies and NDVI anomalies. I have to say the NDVI anomalies are from MODIS, but they were resampled to the ASCAT grid, so they're at 6.25 kilometers, whereas the Sentinel-1 is at a 500-meter resolution. And we can see that we have a very strong correspondence between the Sentinel-1 drought indicator and the NDVI anomalies as well. So this is very, let's say, yeah, it looks very good to use Sentinel-1 for high resolution monitoring of drought conditions. So to conclude, validation is not easy in remote areas or anywhere outside of Europe, the US, and Australia, especially because we're lacking in situ data to have at least some indication of what the true soil moisture conditions are. What we do see is that soil moisture provides reliable and complementary data for drought monitoring applications. If we look at precipitation and surface temperature, NDVI and soil moisture, we can really see the development of a drought. And also that we can see Sentinel-1 is very promising for example, decreasing basis risk. So we have a higher resolution soil moisture product so that we can get even more detailed information of where drought is very severe, for example. But also more research is needed in the development of the algorithm, and also the effect of subsurface scattering. So scattering from very dry soils or deeper soil layers is still needed. And to give some recommendations, so I really think that as an Earth observation community, as hydrologists, we really need to come together to provide recommendations on products, because we have too many indicators. We have a lot of thresholds. We don't know exactly how they relate to impact in, let's say, in the countries. Also because the impact data is very often not shared by governments, of course, so it's very hard to do this. And we really need to do that Earth observation data can be used for decision support. I mean, we as scientists can do a lot of research on droughts, but in the end, the data needs to also be usable for, for the government, for the World Food Programme, etc., etc. So evaluation with drought impact data is needed, but not always possible. And collaboration with stakeholders is needed to really build up the capacity there as well, for example, in Mozambique, so that they can use satellite data as well. And also that we can learn from them in terms of, let's say, drought severity, drought impact, and how this is represented in our satellite data. That's it from my side. Thanks.
Thank you. Are there any questions? Yeah, please.
Thank you so much. Yeah, that was really interesting. I was just wondering, but actually that's not my question, but if you go a couple of slides before, with the time series of soil moisture and precipitation, they seem to be almost anti-correlated, right? Is that something wrong with the precip, or?
No, this is not precipitation. Sorry, this is on the red one, the bars, the red bars. This is the.
That's the SMAPI in the.
Yes, the SMAPI.
Right, I see
the drought indicator.
Yeah, sorry, I see the axis now. No, my question was about your plans for seasonal forecasting. If you mentioned it at the beginning, but yeah, do you have plans for that?
No, this was actually so the project that we currently have, which is funded by the Austrian Ministry of Climate and Energy and Innovation and the Austrian Development Agency. In this project, we were only gonna do, let's say, monitoring and let's say get the user requirements, etc. So it's really a startup project basically in this direction in Mozambique. But we found out that a lot of, basically everyone wants to have predictions. And this is something that now we need to look into. But in this project, we actually didn't have a budget for that. So I've started with some master students to start some. But yeah, this is definitely something that is very much needed. And I think there we also need to work together with the modeling community in terms of forecasting. So I think that's definitely an idea for a project that could be done. Yeah.
No, very nice. And I believe that we should move away from all these indicators and try to, because actually the user doesn't need an indicator, but they use quantitative information like, I don't know, how much water is available or something like this. Do you think that, because actually using different products, actually we are applying vegetation, so most of surface good zone, where we can go, we can try to get this target. How far we are? What do you think about that? Is it feasible?
I don't think they need information on how much water is available, because as far as I now realize in the projects that we have now, they prefer to have one indicator that tells them if they need to take action or not. Yeah. I think it might depend on with whom you work and which country, but let's say the level of information that they want, so far they would be happy to have basically qualitative data. And then, of course, for example, in the World Food Programme, they have their PRISM platform where they do provide data, and which also some of the Met services are using. And they are then really just using precipitation data, and they will ingest the soil moisture data as well. But there they are actually then staying with the with the variables themselves. And then they actually prefer to have only anomalies, for example. So it's a bit, as far as I now am learning there, is that either they want some qualitative data or they prefer to just get the soil moisture data, for example, and they add it to their own system. Yeah, but this is for Mozambique. So yeah.
Thank you.
Thanks.
All right, thank you, Mariette. We move to the last presentation by Christian Massari, again from IRPCNR, working on depleting groundwater in the Po River Plain, Italy, as seen by observation from grace and vertical land motion.
Thank you very much, Francesco. Good morning, everyone. This is a study that we carried out along with the University of Berkeley, and it's led by Grace Carlson and also other universities of United States. And it's basically a problem that we had in the recent drought in Italy that also Angelica mentioned at the beginning. And so basically, in 2022, Italy suffered its worst drought in some evidence, say 200 years. So it's quite a huge drought, this one, that we experienced, that we have a very low snowpack. There are also a contribution of Francesco that this is under review that highlight this. And we have many evidence of surface fluxes and modification of them, but very few of them about what happened in the groundwater. And so in this study, basically, we want to just focus on it. So the idea is to try to analyze the long-term behavior of groundwater storage in response to this long-term climate variability and abstractions in the Po River Valley. And we basically, to do that, we used not only satellites, we used more than 900 wells in the area. And we use also GNSS, GPS measurements of the land motion as a proxy of groundwater depletion or recharge. Just a few words about the study region. This region basically is the highest percentage of irrigated in Europe. And in Italy, it provides economic, so it's mostly 50% of our GDP, mostly, and 1/3 of the agriculture that we provide. And basically, irrigation comes mainly for surface water. We're talking about from 70 to 80% of surface water for irrigation, the rest from groundwater, which also supplies domestic water and industry too. But yeah, mostly is for surface water. But so we don't know actually groundwater how much is important. Well, we know that in future will be important because so the recent trend in climate will have less snow in the future. So less snow means also less surface water, and then as an alternative sources we will have groundwater. But we need to understand whether it will be available or not. We use a similar approach of presented yesterday by the GTA rigger. Basically, to understand the groundwater storage, we remove from the total water storage anomalies the signal of soil moisture storage, surface water, and snow water. In this case, we just used one model for snow and soil moisture. Of course, we are trying different other models to try to understand the uncertainty between the choice of these states. And so beyond that, we use the surface water from lakes in the area that are monitored, so the real data. But actually, the majority of the contribution here is from soil moisture. Why does snow actually as an input, but less than soil moisture overall. This is the groundwater signal that we reconstruct in black and using the formula that you saw before. And basically on the bottom, you can see the SPI index, which represent basically the drought condition or the wet condition. And in red, we extract the long-term behavior of the groundwater by using a wavelet analysis. We focused on a frequency larger than 2 years. So it should represent basically the long-term variation of groundwater in the area. We identified three main periods in this 23 years that we analyzed. Basically, the first one where we have a decrease in groundwater, mostly overall 5.6 cubic kilometer, something like that. And then we have a recharge of about the same amount. And then in the last 6 years, basically, we have a huge depletion groundwater, which is approximately equal to the domestic plus irrigation water withdrawal in 1 year. And we have not only the 2002 drought, but also there were drought at the end of 2000, mostly 2007 and 2012. So lots of different droughts in the recent 23 years. And so we try to understand whether these data that we extracted from GRACE agree with the wells that we selected in the area. We interpolated wells water level below, and you can see for the first column, for example, the period 2003-2007, and you can see that there is a similar trend detected by GRACE and the water levels of wells. Also on the recharge period 2007-2014, we have a recharge both identified both in situ and GRACE. Also, we focus on single year, for example, 2012-2014 was very wet, and we try to see also the pattern of the wells and the pattern of GRACE, which actually agree. So this also means that the other contribution of the water cycle that we select are not so wrong as one could imagine. And then this is the last period, 2015-2022. Which is, as you see, pretty red. And so one of the questions here is whether we can recover from this period. And so we just analyzed a period of recovery, which is 2007-2014. We can see a double peak here. We have a recovery up to 50% in the first part. Then we have a drought in 2012. And then, so the groundwater depleted, and then we have again 2 years very wet, where we have an increase up to 90%. So it recovered almost everything with respect to the previous period. So to understand whether we can recover in the future, what we did is a very simple approach. We fit the non-parametric probability density function of the previous recharge period. And we assume that in the future, there will be different combination of this using Monte Carlo. So assuming that in the future, we will have only recharge, so as a best case scenario, so it will rain a lot, it will snow a lot. But even though, if we assume this, we noted that we'll have from 11 to 28 years to recover completely from the recent depletion, which I think is very alarming for this area. Then we wanted to look also at the vertical land motion because GRACE is very sensitive to the water mass. But if you have a confined aquifer, actually we don't have a mass change, we have a pressure change. And so basically, probably GRACE is not too sensitive to that variable. And so we look at the land motion. Basically, to understand how we analyze this, we have to understand that we have different forces acting on the land surface. We have there is equilibrium, so total water storage anomaly is 0, and we don't have displacement basically. Conversely, when we have recharge, we have two forces. The first one is the weight of the water mass that created actually a displacement, downward displacement. And also we have the aquifer, the poroelastic deformation of the aquifer, where we have an increase of the pressure, and that for the theory of BO, which is a theory study in geotechnology and stuff, we have an increase of the deformation, so uplift. If we have discharge, then so we have a period where the total water storage anomalies are lower than 0. Then we have subsidence for the poroelastic deformation because we have decrease in pressure, and then the aquifer actually provide a reduction of its volume, and then an elastic loading then actually that compensate this. So the balance of these two forces regulate the proxy with the groundwater. So sorry for this, but it would be important to just highlight this because to have to better figure out what happened. So here are the vertical velocity that we observe in the period 2000 to 2003, 2022, and you can see over the Alps we have basically positive displacement, while over the Po Valley we have subsidence. So this actually make us think that there is a problem of water abstraction, loss of water in the valley that actually create this subsidence. So this is a known problem for the Po River Valley, actually, from the 70s. It was studied by the Gambolati et al., a very recent paper, famous paper too. So we try to correlate the GNSS displacement with the Grace-derived elastic displacement, and we see that actually they agree very well. So meaning that most of the points that we selected, probably the contribution is from unconfined aquifer, but there are some spots, some points where we have differences, basically an inverse correlation, especially on the valley. This is the long-term signal on the left, which is from 2 to 10 years frequency, and is the annual on the other side. So basically what happens, the difference between the 2 points here from the top is a point on the Alps, for example. You can see a lot of good correlation between GNSS and Grace. So on the other end, below, you can see that we have the blue line is Grace, is not really correlated with the GNSS, which is actually correlated with the groundwater level. And this means that this actually is a confined aquifer where we have we can catch with Grace the different dynamic. And so we removed, for this reason, the signal of Grace, the elastic deformation of Grace of the water mass from the GNSS, and try to understand whether the GNSS signal agrees with the water level of the wells. It's very difficult to see, but there are some spots that have the gray edge, and those are GNSS, while the others in red are interpolation of wells. But it's important to just understand that both periods, the depletion from 2015 to 2016, and the other one, the signal of the water level, I mean, is consistent with that one of the GNSS. So GNSS in this case can be used to provide information for groundwater depletion in the area. Also, it's important because it has basically a local information rather than very large information as Grace has. So to conclude, some recommendation, and so we try to understand whether we will have a recharge in the future, whether we will be able to recover from this huge drought. And so what we found that it's pretty alarming, because the best case we have 10 years. And so if we have to consider this groundwater for the future as an alternative source of surface water, probably we have to take care of this. And so technically, Grace is useful also in the small area, even though we have to also understand the problem of leakages and other things. And also the poroelastic deformation is something that we have to consider when we analyze GNSS, and it also can be very useful for confined or semi-confined aquifers. Thanks a lot. I'm done.
Thank you, Christian, for your presentation. Do we have questions or comments, please?
Very nice presentation. Just a quick question. When you say recovery, what was the baseline for that? So you have a data for 2002. How can you be sure that this state that you have during this time period is the state that you want to get?
Yeah, this is true. I mean, the period that we analyzed, it's not very long. Actually, it's 22 years. And so this is something that we have also to consider in the future. What we know is basically that this period from say about 2000 to 2023 is also very low with respect to the previous period, the 1980s to 2000. And so this is something that we should consider. But so even considering these, I mean, it's pretty alarming. Probably this is also a pink situation of what is really is if we consider the longer periods.
Oh, yeah, please.
One comment about these years that you mentioned in the second comment.
Yeah.
Do you think these years is too long for groundwater recovery? Because we know that this water is there and for many, many years. So if you say that in 30 years we can recover this groundwater, I think based on the scale, it's really a short period.
It's short, but we consider mostly surface aquifer, and so we don't consider wells very on the deeper wells. Okay. So it is probably that in that condition actually this is short, but it is also the most easily accessible water, no? And yeah, of course, this is another.
Thank you, Christian. It's a very strong message you're bringing. So also the question, like when you, for example, compare what happened now in California, this extreme wetting up, did you have anything comparable in the Po Valley in, say, in this period when there was a wetting up?
Yeah, what happened in California, I think, is also talking with JT Rigger yesterday, is that in that case, actually, there was so much snow in so little time that actually the recharge was impeded, so was avoided by the runoff. I mean, much of the water ran off. And then in that case, that they couldn't have that kind of recharge that they needed. So in this case, there is a much longer period, just not 1 year. And so probably if we have rainfall year by year, then in that case, there is more chance that the recharge is effective, not in the case of California. So this is the difference in terms of time scale, basically, in this case. But of course, it can happen. Then the climate is also a bit different. That in California, probably there is much more evaporation than in the Po River Valley. And this is another issue that we should consider in case we want to project. So these are only numbers, but we have
but important numbers.
Yeah.
Hi, Christian. Still thinking about the GNSS, but I'll talk to you about that later. But no, my question is about this is a long period, right? Like 1 to 3 decades. So do you consider the change in atmospheric demand, but also societal demand for water when you calculated this period?
This PI, you mean when? Sorry, I didn't understand the.
Well, I mean that if you consider the following 30 years,
Okay.
Potential evaporation is going up for sure in the Po Valley, but also societal pressure on water resources is going up, right?
Yeah. Yeah, no. With the approach we followed is very simple, and it was just to give a range of the groundwater scale to recover. Of course, if we have to send a clear message, a more precise message, we have to consider maybe projection of groundwater model in the area, and also something probably connected with atmosphere. Because there, I mean, the area is very critical. There are a lot of water abstraction, irrigation, that probably the land-atmosphere interaction are very intense. And yeah, this is a good suggestion, actually. Yeah.
Also, one question regarding the vertical land motion. You showed this picture about the 500 stations you had for Italy, and there you could see that one before, this one, and you could see the increase over the Alps. So I would assume, is it the increase related to deformation, plate deformation, and
Yeah,
not really the groundwater signal?
exactly. This is what we assume, and that those deformations could be probably also on the less snow in the recent periods, and so there is actually an increase in the land surface because we have less weight over the land.
Because I would assume all the water is not going there in the groundwater, but flowing in the
yeah, even because the snowpack is less than yeah. So I mean, we should go into details on this, but yeah, this is what we assume it happened.
Thank you.
Yeah.
Thank you, Christian. I think we still have about 13 minutes for a general discussion. So I think we prepared some seed questions. I'm going to take. Let's see. Okay, so looks like we have a problem with the PowerPoint. It says that we have PowerPoint cannot read the presentation. Well, anyway, we tried our best. But we still have some time. If you have general questions, general feelings about what we have discussed this morning, we have time. We have time for that.
Maybe some of the questions were, for example, that we ask ourselves, because the session topic is water for the society, and I think we have seen a lot of products and results here, and I think the society has to get let's say an easy access, or they should get a guidance how to use or which data they should use very well. Because if you're in the community, you have the different data sets, you know about the problems, advantages, disadvantages. But if you are not in the topic and you would like to use the data, for example, as the soil moisture, if you are from the stakeholders or so, what is necessary from us to give them at the end a product where we say, okay, this can be easily used, and yeah, so what can we from our point do to give a consistent product to the end users, let's say, for example.
Should I take a mic?
Yeah, better.
Thinking of the staff, about what information is needed for the quality data and that's a lot of stakeholders. I was thinking of a project that happened before the hospital forward. So we ended up with a WhatsApp extension where people would get read. Right? So I think that depends a lot on the stakeholder.
Just to follow on that point, so we had a similar thing in India where the stakeholders are local farmers, but what really helped was having a third party working with them. So it was an NGO, and it comes down to, yeah, what do they really want? And actually that mix of indigenous knowledge, and it was around water use and things like this, made a big difference. And then having the experts visit and speak with them, it's quite a nice activity to do. And it changes your perspective a little bit as well. But I would just echo those bits are really, really important. And they're quite hard sometimes to find those partners, but yeah.
We had a science that's pushing the what is not finding them finding them one type of business probably is the kind of increase demand and so there is something about hey, take care of that. Your use of technologies and then all recently the timing of last year that it's more than what we need to do. Carefully looking at the timing is 100%. Not all, of course, going in some cases, and then so they have to make action, depending on the follow.
Yeah, I would So maybe a comment on that, like you definitely calculate one again. I don't know. I have a couple of examples. In which the barrier was sought between what we were producing and what stakeholders needed. It was easier to make it right. So I think it depends on what stakeholders you talk to right now. You're talking to governments, for instance, not saying that governments are particularly but yeah, the farmers, many times they just prefer something that is really probably not with $50. Because then we find that I think you have to know something that very big group also if we don't have consistent maps, what's the name? They say, I need a lot of water. If all one comes down, they could be having one policy discussions and it's the whole complicated. Some of the deals, probably know European has, which is the agriculture service, is required to provide weekly maps of long-term goods. If not something was to have one observer or one monitoring economy who would provide them 5 levels, whether it is sufficient, deficit, or very high, whatever. For finding a lot of system season, you may go on one day, if you're a number, then you does not go all the way to the neighbor's backyard and say, hey, but you drive. You have patches all over the space on that, where you provide with more quantitative observations if you want to move to a quantitative. But it should be more sense. I can do the logical side, so I'm a methodologist. One of the things that we have been doing or trying to do, not to get just color from green to red, just that line. We are aiming for the mismatching, where you have probability and intensity. Applying to the job. One of the things that I can reach that you have all these indexes, or you have going to over the highest probability. So you provide a color, but you can take care of the probability in that one, mostly that and that probability. So that is something that you can decide, and it's not so straightforward. And gives information to the user, which must know how to use kind of. But it's something that we are trying to do more and more in the knowledge side. And I think it applies also to the this file. It's not also perfectly even and trying to answer that question that you have so many, we know that for many topics in science, you have so many indexes, how do you treat them, right? So probability, we have examples of models. Maybe we should also consider some of the products and try to work with example, not only on models.
I use the microphone. Yeah, so I'm going to say maybe something that people don't really like, but we're still all sitting here. We're all still scientists that are now basically discussing what we think the users and the stakeholders need. So in the end, I think what we need to do is really work much more with the stakeholders and involve them much more in our science to get an answer to this, because we can keep discussing and have different opinions, but in the end, they can use our data, but they can tell us also what they need exactly. And it can be quantitative and qualitative, as Jago said, and as said before, depending on which stakeholders you're working with. So I think we just need to collaborate more with them on that.
Mm-hmm. Yeah, if I can also comment on that, I think we focus quite a lot of stakeholder needs, which is obviously important. I think our experience at least is that we can also learn a lot from these people. In our case, we run a national monitor chain for snow water resources where we issue deficits, and we try to project what that means in terms of summer water supply. When we go out and talk with the agricultural people, for example, we ask them, would that be useful for you to know? And the answer usually is that we already know that. We already have our systems in place, sometimes very naive, looking at they have painted levels on their water tanks, or they know where to look in the mountains and if there is snow there or not, then they decide based on that on what to grow. So therefore, for us was an enlightening experience. We of course we have to discuss with them, but my invitation is also to try to learn from people, because they often know quite a lot of stuff that is useful to us.
Yes, since we work together, my intervention was more or less what you said. I agree with what Mariette said. How my experience working with stakeholders, especially if we talk about drought, is that they want to move from the hazard, like an index expresses, to an impact. So how we can link another level, like the soil moisture anomaly, indicate us to an impact, how many people will be affected, how type of crop will be affected. And to do that, we need more, something that I think is missing in my experience. So an impact database on drought, and try to link the hazard to the impact, to give to the stakeholder, let's say, a numeric answer to their needs. So this, from a scientific point of view, a step we need to take to, let's say, improve the efficiency of our research. So there is an experience project in which we are involved as CIMA, is the DORA project. We, together with JRC, we try to build a drought impact database as at a European scale, but this is something that's it's, let's say, beginning with, should think more how to link the hazard that we are seeing from satellite with the impact as well.
ground, we have these colors, exceptional ground. Something that we should consider that 100%. So many of us warning the data of satellite and satellites, and you have data from 2003, and we know that the last 2 decades was a time when there is many events, and maybe we were underestimating or overestimating take a longer time. And we would provide this information to the stakeholders, say that we would have exceptional ground here for mobile situation, but don't explain we get from ground. And for them, it's really and the last information. It's normal, but if you consider the longer time, consider the whole, in some regions, maybe it's really ground. So at the level of the moderate ground, but we don't consider that. So one point is for precipitation community, it's easy to go back in time for some very satellites and stuff like this. But just consider that these are just presenting. And hence the time period.
Yeah, I think it says what's going on actually. Because -1 it started to go with the stakeholder by then in that case changed because I mean those guys take actions patients in Flores maximize the data. It's required process that probably what we have performed is to trigger this process with that point.
Was one last comment, I think. Budget. Mm-hmm.
O'clock. What? Yeah, this is great. But why is it slow? Yeah. How's everybody doing? Good. That's great. It's right about 2 o'clock. Ouais, pas mal. So, on behalf of my good friend Guy and myself, hello, hello. Welcome to Wednesday afternoon. You're still standing. It's hump day. You're doing great. We're very proud of you. We'll need you also in an hour and 40 minutes to help with the brainstorming session. All right. So if you do your digestion, do it before. If you take a nap, I'll wake you up. But we have amazing speakers today, and Guy and I have decided to use a very scary alarm at 18 minutes to let you know that you're running out of time. Okay. And if you pass your 20 minutes, we'll thank you with a big round of applause, and I will escort you back personally to your chair. All right. And is there anything you'd like to add, Guy?
No, not now.
No, but maybe later we look at a picture of the big flood because it's important.
Yes.
All right. Without further ado, we have Adrien, Paris. Welcome. The floor is yours.
Thank you, Cedric and Guy. Good afternoon, everyone. Well, I know it's post-lunch, so I won't bother you with mathematicals and so on. I let this for my colleagues that will present later in the afternoon of tomorrow. But I wanted to show you a little our vision of what can be and what must be, in our opinion, operational monitoring of rivers. And we will show the case of the rivers of French Guiana. So for those who don't know, French Guiana is this little territory. It's a French ultramarine territory, so it's still France. However, it's in the Amazon biome. And it's populated with almost 300,000 inhabitants. That's what is interesting, that live mostly on the coastal and riverine area. The rivers there, they have a huge importance for these people because it's their way of finding food, of transporting goods, of transporting cars, gas oil, and so on. And it's a territory with several issues, mostly due to the transboundary water management issues, because it's not always easy to communicate and to collaborate between several countries. And in the case, it's Brazil on the southern part and Suriname on the northern part. So, and in French Guiana, during the last years, we have seen more and more issues related to water resources due to pollution, illegal mining on both French and Surinamese side. Really critical floods in the 2 or 3 last years. We have had 3 years of really incredible floods. And this year, due to El Nino situation, really strong El Nino, we have seen really severe drought, which is impeding people to reach their home because they mostly use these little canoes, and the little canoes cannot pass anymore on the rivers. So really big issues with water resources. There is in French Guiana an in-situ monitoring network, which is, let's say, operating and not that bad for this kind of territory. We have almost 15 stream gauges, but only on the French and Brazilian side. We don't have any information from what is coming from Suriname. And what you can see here is that those gauges are not always made for really severe droughts, for example. So this is last week. You see that the gauge was not in the water anymore. So we don't have any data, or we have really strange data that is not useful for the monitoring. And in French Guiana, since the last years, there has been several initiatives, including SWOT Calval. So the Maroni River is a tier 1 SWOT Calval site. So we have implemented a lot of methodology and of measurements on the river, and also in the frame of ESA Street Art project, where we have installed more gauges and performed more measurements. So now, given the situation, how do the satellite data can be used and help this kind of territories? This is what we intend to do in our operational platform. This platform, we want it quite simple. So it's fed by Earth observation data sets. Obviously, we talk about radar altimetry. So what is already available on websites like Daiichi and Hydroweb. And also, we also investigated improved retracting methods. So you can see Malik's talk this afternoon. You have the main input for hydrological models, which is the rainfall from satellites. So several constellations then. We use mostly the GPM mission. You can see also a talk that I will give, but it's Romulo's work. And we have a lot of other database from space, like vegetation cover and so on, DEM and so on. We also, as I said, have in-situ data. So we use this data for model calibration. We use a special IDCP that we made just under the satellite ground tracks to derive heighting curves and so on. This is what Laetitia will show tomorrow. And we have also, thanks to the SWOT Calval, several longitudinal profiles that helps us to check models' consistency. So we embed all this data inside the MGB hydrological and hydrodynamic model. So it is calibrating against in situ and altimetry data. So if you want to know more about MGB, you can see Laetitia and Slee talks. And inside this model, there is an assimilation framework, which uses the Hansen-Kalman filter, where the data from altimetry can be assimilated to correct real-time estimates of the discharge. All of this is embedded in a Python scheduler that is run in real time and with a few day steps of prediction. So this gives us this platform, which is called SAGI. You have the acronym, it's a French acronym, but which provides for the entire territory, so the 10 biggest rivers that flow into the oceans, the current state of the flows, and short-term predictions. So it's based on real-time rainfall estimate, and it's corrected at each time steps, thanks to radar altimetry. And what is also interesting is that we co-designed with operational agency on the territory alert threshold that can be triggered when the water level or the discharge reaches a threshold. So if you have a look here, you can see that it's almost all red. It's normal because as I said, there is a strong El Niño this year. So all the rivers are in drought situations. Those that are the arrows going up, it's a graphical bug. But all the rivers now are in drought due to El Niño. We have a lot of publications of this critical condition in South America. You may have heard about the Amazon with dolphins going to dead and so on. It's also the case in French Guiana. And if we look further on a given location, you can investigate it provides, so for each location, each one of these locations here and all the drainage network, information of discharge, what you have here in blue, and the difference between this current state of the basin and what is normal in a given period. So we have made a long-term run from 1980 to today, and we can compare the situation of today with something that is the main situation in the last 4 decades. So you can see, since we were last week on the field, we had the opportunity to validate the estimates. So you can see that we sampled almost 60 CUMEX, and the estimation of the model in real time was around 55. And again, what is interesting is that it can complement the in situ data that for this period, that is because of the severe drought, wasn't operating well. You can also see that at this location, since it has begun to rain in the last day, you can see that the model is predicting an increase of discharge due to the time propagation of the flows. And so we were here on the first window. The second window here provides the alert, so the discharge alert. These alerts, as I said, they were designed together with DGTM, which is the operator of the in-situ network. And what is interesting is that you can see that even though we are in severe drought now, you don't have alerts everywhere because they don't have alerts designed on each location because sometimes there is no population or no problematic of drought. But anyway, we were able to design customized alerts that can be updated and probably will be updated in the next years because the conditions are changing and the alert levels change together with the historic of flows. So to conclude, this platform and these embedded methods, they are quite cheap and easy to reproduce in any territory. You have where you have rainfall data and altimetry data and the capability to put a hydraulical model. We use mainly open source data, and all the information that is produced by the platform can be accessed by anyone. So even the research agencies, but also the operational operators on the field, and even the guy who wants to know if he can navigate tomorrow or not. And the idea is also that it can be provided to the community through, for example, HydroWebNext or this kind of platform that can come push the information and provide in a broader community. Concerning this work, our next steps will be to obviously include other observations than nadir altimetry. So I'm thinking about SWOT. The system is, or assimilating system is already more or less ready for that, but we still have to work a little on that. On really interesting points like near to the cities or the coastal areas, we should and we will embed this with final resolution hydraulics. You can see Kevin's posters or talk who talks about that. And for the forecast, so if we want to extend a little the time, the anticipation time of the forecast, we will include the operational meteorological forecast as forcing. And since we have to make recommendation, my recommendation would be that in all of our applications in terms of spatial hydrology, we must use a multimodal approach. It's not a single model that will solve all the issues, but more the complementarity between several types of models, global ones, regional ones like MGB, or even local hydraulics that will help by being merged to solve the issues that we can find on the place. Something that is really important for me is that all this implementation was only possible because we had SWOT Calval, we had Street Art Project, and we had a lot of in-situ data. We still go there. We were there last week and so on. So it's really critical on this kind of point to have an information from what comes from the field. And last one is that, in my opinion, the frequency and the latency depends on the basin, but what doesn't depend on the basin is an information of long-term time series. For example, now with altimetry, we can reach more than 30 years of information. And this kind of information is critical to understand what is happening in the basins and how we can mitigate this kind of changes. And I think that's all for me. Thank you.
I didn't mean to scare you up this much, but you gave us 7 minutes of conversation, which is wonderful.
It's the best part.
Yes, yes, it is the best part.
Any questions? Because we got quite some time now. But,
I definitely have one.
Yes.
When you say you use HydroWeb, when you say you use, thank you, you use HydroWeb altimetry and assimilate that within MGB. What do you mean exactly?
So in this concrete example, the platform that is running, I previously estimated the rating curve using a previous run of my model. And so I convert the water surface elevation into discharge. But we already have made studies and it's almost ready to assimilate directly the water surface elevation when it's available and switch to discharge when it's not.
That's great. And then the assimilation methodology, is it direct insertion? Is it Kalman filtering?
It's Kalman filter, yes.
Very nice. Thank you. Other questions for everyone? Would you mind using the microphone, please? Thank you.
Thanks a lot for the shortened presentation, really appreciate that. I was wondering, you talked about co-construction. What was your experience there? What were the kind of concerns that you felt were being voiced by the operational met agency you said you worked with? Yeah, I would really love to hear your thoughts on that.
Yeah, I think it's a good question. Actually, the first point of this co-construction is that we were there a few years ago and we had to find someone that knows the field, that knows who to deal with, because it's not our territory, we don't know the place. So, and we were put in contact with this operational agency. So they help at the beginning. They help a lot with finding who to drive the little canoe and so on. And then we discussed further. And for me, they helped understanding the problems of the territory. Like I didn't know that on some locations there was no need for alert for drought because it's not a problem. On some places you have 3 levels of flood alert because there are a lot of houses and schools and so on, so they have to be warned gradually, but as soon as possible. So it's really on this kind of information that they help us understand, and then I know that the system we designed fits in their need. It's really this kind of trade-off, which is really satisfactory.
I have another. So it's very interesting, and also in view of the swap mission and other.
If maybe you can let him finish his question, and then we'll have yours. Thank you.
But sorry, sorry, didn't see that. Very quick question. So because of all satellite missions, it's quite important that you said that the discharge data will be open for science. How do you go about doing that? Because it also means that the system has to really stay in place for a while. So, you know, who is operating that, making sure that the data, that the discharge series actually, that, let's be honest, that it doesn't happen what happened to JRDC, you know, the global river, because people stop gauges. But if you do this as part of your effort, is really amazing. And I think we need more of those where people build these things, but then making some of the data really free and open. So I wanted to have your thoughts on that. What is your plan for really doing this?
Okay, but one more good question. Yes. So this platform was built in the frame of two projects, two small projects, which were the two first one of our company. And in this frame, in the frame of this project, that was funded by CNES, we said, okay, for few years we managed to maintain this platform, considering that it remains the way it is. So it's deployed on low-cost servers, and we can manage the maintenance for really not that expensive cost. Okay. Now, what is the consideration that we have to have is how do we fund the other steps of the research that I mentioned, maybe hydraulics, maybe better forecast, and so on. And on all these steps that we want to try to find funds for them, we will keep a part of the funds to keep the maintenance of the platform. For now, it's the way we can operate and ensure that the data is being provided.
It's a good plan. Yeah, thank you.
Yeah, thank you. Sorry, I meant to say that we'll sort the questions in order of distance from microphone. So if you want to be first, just run to the microphone. Go ahead.
It's okay. Thank you to finally have an hydrological model in this session. We make this kind of things to this kind of platform. So the previous question was very, very interesting. My question is about, you say you have ungauged basin also. How did you assess this issue?
Yeah. Indeed, we have the small basins near to the coast that are ungauged. For them, we use the regionalization rules, like considering that given a similar state of the basin, like similar vegetation, similar soils, the parameters of the model should be more or less the same that its neighbors in the same conditions. And then we validated again against what we have, so radar altimetry. So we know that in this location, the model is good in water levels. And since we know that the geometry and the soil is representative of what it is, we consider that it's also good. For now, there are some places we never were there. We didn't have the opportunity to sample, but we also work with OEG, and they can make further measurements on this kind of rivers to ensure that the model is good, and if not, to help tuning a little.
Thanks. It's a global model. It's not a distributed one MGB.
Yes, it is distributed.
It's distributed. Yeah. Okay.
Adrian, thank you so much, and great to show us an example of how to foster a good conversation by finishing early.
Thank you,
so
thank you, everyone.
And next up, we have Antar Dasgupta.
Super.
Thanks a lot for having me. I think it's really great that I talk at this session, which is chaired by Guy, because this idea actually stems from this 2019 commentary that Guy wrote on the need for accountability in flood mapping. I realized that this conference is really more, people are showing products, algorithms, things to derive from satellite data. But when we do that, we do need to benchmark our models. We do need to validate our models. And one of these validation questions also comes to flood mapping. And strangely, we do not yet have best practices for this, while we do have them for more or less every other remote sensing application, most notably land use land cover. So in collaboration with one of our students and a really sort of big name in the land use land cover community, we tried to come up with similar guidelines for flood mapping. And what is the problem? I only go through this because the flood mapping people already know it, but there's not so many flood mapping presentations here. The problem is mainly that we look at binary classifications, especially when we look at flood mapping, and the differences are not big. So always there is this problem that the common area or the area of overlap will mostly outweigh the area of differences. And of course, when you look at automated mapping solutions, you look at this huge satellite tile, only a part of which will typically be inundated. This means that we will always have a much larger number of non-flooded pixels than we would have flooded pixels. And therefore, the common accuracy assessment metrics based on the confusion matrix that we use, they were all defined for multi-class classifications. And so when we try to use them for class imbalance binary classifications, we do not really get where we want to. And what this leads to, I think many people or many seed questions at several sessions talked about uptake from users. We form the greatest barrier to this uptake because the users do not then trust this data. They find when they test it themselves, the algorithms that are published in literature, that the accuracies are not consistent across different geographical regions. They find that sometimes it's not as accurate as reported in the paper, and therefore they very rightly question what they're being given. And so we try to demonstrate, because, well, seeing is believing. So we try to demonstrate what exactly happens and how this looks across when we evaluate our accuracies across a variety of different study sites. And we selected 5 completely different study sites ranging from India, Mozambique, Australia, some really large flood events, some relatively smaller ones. And we tried to see synthetically, using controlled errors, how this could look. Excuse me. So what you see on the screen here in the blues are the the negative errors. Excuse me. And in the yellows, you see different ranges of negative errors, and we've separated them out by different percentiles. And we use a synthetically generated map. We use an Otsu threshold. You guys.
It's very nice. Big guys.
Thank you. I love this community.
Sorry, we're just guys. I mean, whichever guy went up, you should thank him because we missed it.
It was my co-presenter, like the one before me. Anyway, so synthetic maps. So we started with a synthetic map and we control the errors in both directions, and we use percentiles so that we could assume that a mostly equivalent number of pixels transfer the category in the confusion matrix in every class. And we have a negative synthetic error threshold and a positive synthetic error threshold, and we keep it within ±5% to make sure that we're not evaluating really bad maps. Hopefully our algorithms are not that wrong. The one thing I should mention here is that our error is only unidirectional. So we either introduce false negatives or we introduce false positives, and we do this on purpose so that we can understand the biases in our metrics. The validation metrics we use are the ones that you see here on screen. They are not cherry-picked. We basically took every single binary map comparison metric that exists, and we ran a correlation analysis on top of it to not repeat information. We basically pick the most commonly used ones and some that specifically deal with class imbalance, for instance, the Matthews correlation coefficient. And what we tried to do was we tried to balance the popularity of the metrics with the correlatedness. You will notice here, those from the flood mapping community, I see a few familiar faces here, that we choose the F1 score, which is now used more and more as the ML community comes closer to the flood mapping community, but it's quite similar. So the correlation with the critical success index, which is the most commonly used one, is about 0.99. We are in the process of publishing this, so you can get more details on the metric selection there. So first, I want to show you the impact of flood magnitude. This does not come as a surprise, as I say, to the flood mapping community. Normally, what we do is we have a flood map, we have a validation map, we overlay them, and we try to evaluate the match between them. What you see on the screen are on the y-axis different metric scores, and on the x-axis different synthetic errors. And that blue and gray plot at the bottom is showing you for the different study sites the proportion of flooded pixels. And you will see that Mozambique has the largest number of flooded pixels in the domain, and that is the pink dot. What you will immediately notice is that for the kappa score, the F1 score, the critical success index, the pink map for exactly equal errors, the pink dot, is much higher. This means that we positively evaluate those models, those algorithms that flood everything in the domain. This is one thing that I want to show here. The second thing that's immediately obvious is that there is a very large variation in the negative error maps, but not in the positive error maps. So 5% positive error and 5% negative error look nothing like each other. We over-evaluate our accuracies when our maps are positively biased. And of course, this also comes from the flood magnitude. The larger it is, the better the map looks. The final thing that I want to show you here is that the overall accuracy, even though it does not allow you to get a very large discrimination between the positive and negative biases, it does not demonstrate a similar kind of positive or negative bias. I want you to hold that thought as we go forward. So now looking at the impact of sample allocation, here I'm talking about how many samples we need in each class. We have chosen here the equal and proportional because the optimal one requires too much probability to calculate. We could do it, of course, but we cannot expect everyone to do it. So we try to see what's easiest to do, but we should do in order to calculate these accuracies. Here you can see the variance in metric scores observed over 1,000 bootstrap runs for different allocations of pixels or samples in your flood class. The pink dashed line shows you equal allocations, 50%, and the blue lines show the range of the allocations in all the study sites. So we had 5.4% to 10.6%, and you can see immediately that the variance in our metric scores really increases a lot when we are looking at the overall accuracy, for example, as we increase our allocation in the flood stratum. But more or less, the proportional allocation shows a more stable metric so that it's not varying too much as the bootstraps choose different samples inside your sample set. The second thing that we show is the impact of sample placement. We've all seen these different sampling strategies. We're familiar with the stratified systematic, which the stratified random, which we most commonly use. And here we show that for the different study sites, when we try to use sort of systematic sampling, we get a relatively more condensed range of metric scores, which essentially means that we're able to pick more reliable samples, which means that so the bootstraps are not really demonstrating a large variability, making our metrics more stable. Looking at the random one, as we expect, the sort of distribution is a bit more. And what you can also note here immediately is that when we are optimizing our sampling, the trend in the F1 score and the MCC is completely reversed. Now it is favoring negative errors. So the negatives biased maps have a much higher sort of accuracy score. Again, this is not what we are looking for, but that's what ends up happening. So what happens when we optimize sampling strategies? So we look at the optimal number of samples, we look at the right allocation, we look at the right placement. We show here that by doing this, for all the 5 entirely different flood events, completely different study sites, different flood magnitudes, we are able to get the violin plots, first plot top left, completely to align. And this is really not what we could do before. And what we're also able to show, perhaps a little bit provocatively, is that the CSI, the F1 score, what we use most commonly in the flood mapping community, not only are we unable to optimize it, it actually gets worse when you do that. So now it's starting to favor the type 2 errors, which is not what you want. And the Matthew correlation coefficient, unfortunately, also behaves the same way. So what should we do then for our flood mapping? Accuracy assessments very strongly depend on the choice of metrics and sampling strategy. When we want to publish a new algorithm, we do want to understand whether it's performing better or worse than already published algorithms. It is completely impossible to compare the critical success index or F1 score across different flood events, across different study sites, and also sometimes across different algorithms. And therefore, we should be really careful and only use it in a multi-objective scenario. The second thing is increasing sample size indiscriminately to spatially correlated pixels. Here I'm talking about overlapping all of your validation data with all of your map. Not good. It's not helping us. It's not helping us understand where the map is wrong. It also reduces the sensitivity of our metrics, and the good metrics, the ones that are balanced, that allow us to evaluate positive as well as negative biases. The overall accuracy, for example, lose sensitivity in this scenario. Imbalanced metrics do not work super well, and therefore we need to somehow estimate the uncertainty in our validation metrics. I realize that in the probability and statistics community, there's a lot of debate about whether bootstrapping helps us do that. We found, however, bootstrapping to be a sort of cheap man solution to this. So we can use bootstrapping to understand the variability in our metrics, given the samples that we've chosen. And future work will also focus on evaluating the impact of validation data quality. We started to do some of it. We realized we are packing too much into one paper, so we try now to do this as a second part. But what we want eventually to get to is to develop a statistically robust method to bias correct our flooded area, because oftentimes flood maps are used by real people, operational agencies, to calculate flooded area for tasks that require such information. Recommendations to the community. Please think about validation. It's not an afterthought. It's where we should start, by thinking about what we need to validate our products. We need to develop suitable and replicable sample designs. This is absolutely crucial. Anyone, anywhere should be able to download your map, your sample points, and be able to come at the exact same accuracy result. This is not where we are at right now, but it should be possible. And of course, for flood mapping specifically, when we are looking at SAR data, which is most commonly used, it's useful to assess accuracies across different land uses. Floods are water inside a different land use, and therefore it matters which land use we are assessing. And of course, we need a higher quality validation data set. Recently, there's been this huge trend of using emergency rapid maps for evaluating flood maps. Not the best idea. As a standard, the data that we use to evaluate our map should be better than our map. If we do not know the accuracy of the map that we use to evaluate our data, we cannot know that it's better than our map. And therefore, it's not validation. Right. And then to the Earth observation agencies, perhaps these are very young in my career, perhaps naive recommendations, but maybe we could develop as a community some best practices for emergency mapping and develop specific guidelines, very much like the land use community, for different remote sensing applications, where we could, for instance, talk about where to check for errors, how to make this replicable, things like this. And to funding agencies, well, I think they have the power to ask for better algorithm validation and uncertainty assessment, because they fund a number of these projects that develop these algorithms. It's very nice to see some of the CalVal studies from SWOT, where there's really, really thoughtful validation of products, of satellite products, but we do not do the same for the downstream products, and maybe we could start there. Thanks a lot for having me, and I will be happy to take any questions.
You want to take that first question since it was hinted that you might have motivated some of that work?
I have no questions. I really.
Yeah.
Oh, sorry. Yes.
Sorry for the distance microphone. You got it. 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 You got it.
So really nice presentation. Thank you. I would like to ask if you have already some guidelines already available or share articles on that subject. And if you have also like share Python libraries or some tools on that.
Thank you.
Or community.
Thank you. Thank you. So we both are in process. It's under review at RSC. Once it is published, we will also open up the library for, but unfortunately it's an R. But yeah, feel free to translate. And if you really would like, well, we have tried to develop some guidelines, but I think that 2019 commentary from Guy provides a great starting point on what to think about when you validate. Thanks a lot for your question.
Yeah, thanks a lot, Wolfgang Wagner from TU Wien. So it's an important step, which I applaud. But I would also like to consider that you also should consider non-flood cases. You know, it should be more generic, applicable. And if you say, well, we also should look at different land cover classes, we should also push the community to say where flood mapping cannot work. So if you have your results here, you also should like delineate those areas where a priori the physical information is not good enough to derive flood maps and how to deal with this information within the sampling strategy.
Right, but you mean here the exclusion mask?
For example.
Right.
But you need to provide the information. If you want to make a good product for the user, and you rightfully say they must be able to explain the metric that you're delivering, so you need to describe the product in the fullest possible extent.
No, this is 100% accurate. And perhaps I should mention, so from Professor Wagner's team, there is the exclusion mask that now implemented on the global flood monitoring system, where it tells you exactly where the mapping can work and not. Thank you very much. But what the goal of this exercise was really to develop sampling designs which could work. And when we evaluate for different land cover classes, the answer should reveal that it does not work, for example, in arid regions, in vegetated regions, so on and so forth. Of course, the exclusion masks are important, but maybe we could just avoid those areas for our sampling. Because you're not mapping there.
Yeah, it's best practices. So basically, we as a community should go to a point saying, well, where an algorithm can work or not. But
yeah, totally.
It's really good. It's really good because these metrics are not reliable. So it's very good.
No, but I 100% agree with this. And these are very important. I think there are now several papers coming in the exclusion mask category. Super important work. Thank you, Professor.
I take a question.
Go.
And again, thank you very much for staying in time. You were 2 minutes 30 before your time ended, so great. Can I make a suggestion? This is absolutely fantastic, and thanks for picking up on my paper. Nobody ever does read my papers, I think. But anyway, so it would be absolutely fantastic, you know, and this goes on to the point of what Wolfgang said. It's like, could you think of building a benchmark data set? Because you're going to have a community that starts complaining because there is no good validation data for the flood mapping. I think I also mentioned in the paper, it's dangerous to go to the field and during the flood map and get water depth or even the rec marks later. It's still dangerous in some areas to go. It would be absolutely fantastic if you, with your guidelines, you pick 5 areas in the world where you have events that are different, but for which you also have field data available. I mean, there must be 5 of those events. And where you have only very few locations in the map where the case is happening where the algorithms absolutely don't work. So you look almost for 5 cases where nobody could say, well, but there were limitations with my algorithms because they were vegetated areas. So you're also trying to minimize those. Don't maybe include urban areas, but have very good cases, but also where you have field data. Because I think this is all mapped from an airborne sensor or something like that, that is not from the same source as your original map, because I think that's what you were complaining about as well. Like people use SAR-derived maps from the same satellite scene, just using a different algorithm when they validate their algorithm. And this is a bit dangerous to do. So it's just a suggestion to maybe.
Great idea. We actually have this in mind. I'm working to, so what would be for sure better is to have higher resolution data. So we have some data from Planet. We have some data from Capella. We are trying to build this, but we have to publish the points and not the data for obvious reasons. But to your point, there is a benchmark data set currently being developed by Uni Arizona. It's called Flood Planet. They will publish it. It's under review. And so this should serve as a first benchmark. And we will also work on it. Thanks, Guy, for this very nice suggestion.
Cool. Thank you.
That's great. Thanks so much. We need to move on. Can we have a round of applause for the speaker and for the guardian angels with the water? And please remind me that I told the fine gentleman in orange over there that he would get the first question when we get to the discussion session. All right. Next up, we have Florian Roth.
Right. Hi, everyone. I would like to present you our comparison study of VV and VH polarization used in our Sentinel-1 based flood mapping approach. I would start with an example what explains our motivation behind this step. You can see a local flood over Austria in 2018. In the upper row, you can see the measurements in VV, so the VV backscatter. And in the lower row, you can see the VH backscatter of the same times. And you can see that there are some dark patches in both of the polarizations, and those correspond to the normal open water bodies a flood consists of. So where the backscatter is actually low, and formerly the land was not flooded there. What's interesting is what happens in the red box. There you can see that in the VV backscatter, we have an increase, while at the same time in the VH backscatter we have a decrease. And that's a known wetland there. And we see because of the double bounce effect, this increase in VV, which is not impacting the VH polarization that much. In general, the two polarizations show a contrast between water and land. You can see this in this part of the graphics. So we can use them for water mapping or flood mapping. Additionally, we can see that the VH polarization, the backscatter from the VH polarization is generally lower for most land cover types. And as we already saw in the previous example, the impact from the double bounce effect is different between the two polarizations. What's also known is that the wind impact, which roughens the surface and prevents the specular reflection normally responsible for the drop-in backscatter, is also has less impact on the VH polarization. Now I would like to present you our algorithm to detect floods from our Sentinel-1 data. We have of course, our backscatter as an input, and then we compare this on a pixel basis to a non-flood distribution and a flood distribution, and make a Bayesian decision at the end to pick the more likely class. And if you look at this for a single pixel over time, you can see that the actual backscatter time series here with the dotted green line follows our non-flood distribution, the harmonic model, which is used here quite well. And then at some point you have this drop, which can be explained by the flood distribution very well. So here we detected flood at the end. And after this pixel-wise decision, we have a post-processing and can then say where flood happened and where not in this scene. This algorithm is utilized in the global flood monitoring service. If you want to know more details, you can follow this QR code. And we recently published 2 papers also utilizing this algorithm. One important part of the workflow is the water backscatter model, which is used to define the flood distribution. There we collected backscatter over open water and distributed it into 0.5 degree bins of the incidence angle to get also the information of the standard deviation for the incidence angle. As you can see, both in VV and in VH, the standard deviation is constant in comparison to the incident value, to the in situ angle, but in VH it's slightly lower. Then we can see that we have a linear relationship in VV between the incidence angle and the backscatter over water. And we have a similar behavior in VH, but not that well established. Maybe that's because of quite limited energy received in the VH channel over water. The other important part is the definition of our no flood distribution. That's based on the harmonic model, which represents the backscatter seasonality and is defined by static coefficients, which are retrieved from historic backscatter data. As the model has a lower frequency, you can see here the comparison with the time series in both polarizations, then the general duration of a flood event, it's a quite nice reference for having a no flood backscatter. And if you look at this for multiple pixels, can see how our algorithm works then. Here the output of the harmonic model for a specific time, then the actual measurement from Sentinel-1 of the same time, where you can see the flood, and then how the algorithm detects the flood. To compare the VV and VH polarizations in our approach, we made a study and selected 6 different events, and I will show you some details of 3 of them. First of all, in Guyana in South America, we already heard of that site today. Here you can see in A the difference between the flood maps based on VV and VH data. So the orange parts were only detected by the VH-based flood mapping, the green one only by VV, and the violet color is detected from both polarizations actually. And the situation is that we have a river surrounded by wetland and grassland. So the difference in the backscatter from VV, where there are only a few very dark patches, to VH, where we see much more dark patches, could be related to vegetation. So we actually detected flooded vegetation here with VH. From the same event, but a different location, you can see an agricultural area where over the ocean there is wind or waves, which impacts the VV backscatter a lot, while the VH is not that much impacted. And we can also see over the fields that quite a lot of areas were only detected by the VH polarization. And this can be related either also to flooded vegetation or the wind impact in that case. We can also see that maybe not all of the impacted pixels were detected. Yeah, as our water backscatter model is defined based on open, calm water, that's maybe not the perfect tool yet to detect flooded vegetation. So maybe that's the reason why also VH is not able to detect all of the areas here. Then an example from the dam destruction in Ukraine this year, where we also have wetlands around the river. And we can also see that parts of this flooded area is only detected with the VH polarization. Additionally, we can see some overestimation over the agricultural areas, mostly in VH, but also in VV. Here, this happens because the harmonic model is static, and if in a specific year the actual time series deviates a lot from the harmonic model, then we can see this kind of overestimation. But we are currently working on a non-static model to improve here. The last example is from Finland. Here it's a little bit more complex. We see some noise over the water surface in VH. And we see a lot more pixels detected only with the VV polarization, mostly in at vegetation edges or thin vegetation lines. So in this case, we have maybe also an advantage from VV again. To quantify our results, we made an evaluation, and that's basically the approach Antara warned us before. So comparing with rapid MAPIT data and using the CSI measure. But it's a very nice comparison because the CMS rapid mapping results were using both polarizations in their result, and they have a semi-automatic approach, so can get rid of some errors based on expert knowledge. The sites in general were selected based on knowledge of vegetation impact, and they're quite small scale and in some examples. So more challenging sites for our algorithm in general. And you can see that the VV polarization in generally performed better compared to VH in 4 out of 5 sites. Only in Guyana we have a different result, and you saw that there is a lot of impact from vegetation in that site. The conclusion, in general, our approach works with both polarizations. VV performs better over open water, and we saw some advantages maybe with vegetation edges. If you have, for example, because of efficiency reasons, to choose one of the 2 polarizations, then VV is the better choice. But VH definitely provides a benefit for flood mapping. We saw that we can detect flooded vegetation in certain conditions. Maybe it's necessary to include these situations of flooded vegetation also in our water backscatter model. We have a difference when wind is present, and we saw that VH might have more overestimation, or this specific flood mapping specific overestimation over agriculture might be more in VH than in VV. As outlook, we plan to combine the 2 polarizations in one algorithm. We also think about adding it to the global product at some time. And we are, as I already said, working on a constantly updated reference for our no-flood distribution to replace the harmonic model, which could then prevent some of the overestimation. And as recommendations, I listed some of the greatest challenges I see in SAR-based flood mapping. One is, of course, the reference data, which is not specific for SAR-based flood mapping. Here, maybe a better documentation, maybe also including the quality of a product could really help to improve the interpretation of a comparison between different products. And we still have limited sensitivity over certain land cover types. There, the VH polarization could help, or in future also additional wavelengths like the L-band and so on. And yeah, of course, for flood mapping, the temporal resolution of your satellite system is very important. You can easily miss the maximum extent of a flood or a whole event. So this should be considered in future missions, that the temporal resolution is really important for flood mapping in general. Yeah, thank you, and I'm happy to answer your questions.
Perfect again in time. Really, really happy about that as well. But a great presentation. Thank you. Yeah, we have time for questions.
Thanks for this presentation, quite interesting. What could you say about this harmonic approach on arid areas where you have like sandbanks or some bare soil or bare ground that can be sometimes tricky? Is a good approach? Or
so if you use the harmonic model in those areas, yeah, I mean, if something, some effects appear every year at the same time, then the harmonic model is a great solution, because then you define it once and it works for every year. If you have a lot of changes, mostly we see that in vegetation, as arid areas are mostly masked then. If you have those situations, then it's much more challenging. Then maybe another approach is the better one.
So in general, it's a bit robust to this low backscatter situation on sandbanks. It's should you try to find the anomaly, and it's better to have this approach with your temporal reference. So I guess, but I want to.
Yeah. Yeah, if you want to find the deviation from this model, and you have really some effects which don't change from every year, then it's definitely a good approach to use, I guess, also for other applications. Yeah.
Thank you.
Thank
you. Thank you for the presentation. I don't know, maybe it's maybe a genuine suggestion, but did you already look at Pulsar 2, for example, VV and VH data? Do you think that it could help you understand, have more observation with different angles and so on, that could help you understand why sometimes you miss the flood, or why sometimes you think it's a flood or not? I don't know.
Yeah, we definitely will look into L-band data as well. And we have a dedicated project for this. And yeah, it will help also to improve the temporal resolution, and we will see some advantages in vegetation as well. So that's definitely something to look into.
All right, let's thank our speaker. All right, a quick one, but you know, I get to.
It's my first one for the week. So
Yeah, do it.
So my name is Hervé Guézot. I'm working in rapid mapping from Copernicus, even if I also know from working on water and for SWOT. Just to mention a very interesting talk, very didactic. Just some things that when we are ordering data for rapid mapping, we have no such choice of data. We have a large choice, but with not so many options. And in fact, most of the time, we are reduced to use only VV because we are ordering most of the time related, in fact, to a motion of rapidity to be fast. We can order Cosmos SkyMed, Terrasar is in X-band, most of the time monopolarization. So we take VV as you recommended. So from a scientific technical point of view, it's very fine. But from an application point of view, it's very difficult because you can do it only using Sentinel-1.
Yeah, true. I fully agree. And we have the same issue with global flood monitoring. If you add VH, then you basically have double the input data, of course. So sometimes you have to pick the more efficient route then. But let's see how we solve that.
All right, thank you so much. Let's thank our speaker. And next up, we have Luca Pulviranti.
Okay, thank you. This presentation, the focus is on operational flood mapping using SAR data, in particular Cosmos SkyMed in this case, and it describes the activities related to acquisition plans and to the processing of SAR data that should be performed when a persistent monitoring of a flooded area is requested. Sometimes these solutions, the solution we adopted could be considered as not very rigorous from a theoretical point of view, but sometimes it's the best we can do. So the key point is the timeliness, as underlined before, the problem of the temporal resolution. And for instance, when the flood managers plan a meeting, they require to have information about, let's say, the extent of the flood before the start of the meeting. So they rely on remote sensing data. They rely on satellite data to have information in as soon as possible. So the timeliness is the key point. Another point that is most basin, like the Mediterranean basin, floods have often a rapid spatio-temporal evolution. So they are fast, they're moving quite fast, and so they require high revisit frequency and on-demand capabilities. And in Italy, we often use in this kind of application Cosmos SkyMed data. That is a constellation developed by the Italian Space Agency. Few words so about Cosmos SkyMed. We have Cosmos SkyMed, the first generation, that is a constellation of 4 satellites housed in an X-band SAR, which by default provides data in HH polarization. Currently, we have just 3 satellites because there was a failure in Cosmos SkyMed 3. And recently, the Cosmos SkyMed second generation constellation was deployed, and it provides service continuity with respect to Cosmos SkyMed. And in particular for Italy, the Italian Space Agency and the Department of Civil Protection designed the MAP Italy program. That is a program of regular coverage of Italy with interferometric stacks in the strip map mode, that is the default mode. This is an example of the MAP Italy tracks. The strip map mode, we have 3 meters of resolution, and these are acquisition of low incidence angle. So our case study, the Emilia-Romagna flood disk case study, is just an example of the activities related to acquisition plans and SAR processing. This was the Italy worst flood for 100 years. 21 rivers burst their bank. We have unfortunately 15 people killed and thousands of people displaced. And the Italian Department of Civil Protection required a daily monitoring of the flood extent from May 16 to June 3, 2023. And we gathered 33 images, both Cosmos Skymed and Cosmos Skymed third generation and Cosmos Skymed second generation. And in the first phase of the monitoring, we acquired 2 images per day in order to cover the area of interest. And so the activity related to flood monitoring included the collection of a set of pre-flood images to apply change detection, the tasking of the satellites, the calibration and the geocoding on SAR data, obviously, the generation of the flood maps, and also the generation of the water depth maps performed by our colleagues of hydrology department. And this is the area of interest. And so how the first part was the collection of the pre-flood images. The constraints, they should be close in time to the flood depth to avoid that any difference is related to something else with respect to the change of this scenario due to the flood. We need enough images to cover such a large area, and we need both ascending and descending pre-flood images because we got both ascending and descending flood images. This is our archive. As you can see, we have right ascending, right descending, different viewing angles, and this is the most challenging, the most critical aspect of this activity. We have both Cosmos Skymed third generation and Cosmos Skymed second generation, and unfortunately, only 2 Map Italy images were available. So we had to deal with the problem of the different viewing geometry. For instance, with the descending orbits, this is the zoom on the area of interest. We used this image acquired on March 31, this image, April 14, April 16, and April 27. So for descending images to cover the area of interest. For what concerns ascending orbits, we used just 2 images. This one acquired on April the 1st, and this other one acquired on April 6th. So let's move to the flood images. The tasking of the satellites, this constraint, was performed at least 24 hours before the acquisition time. The tasking was performed in cooperation between the Italian Civil Protection Department, who informed us about the area of interest because the area of interest varied in time. Initially, we focused on Faenza, Forlì, Cesena, and Lugo, if you remember the previous slide, and then Conselice and Ravenna. And the Italian Space Agency informed us about the possible geometry of acquisition. Again, some constraints. The images had to cover, the various area of interest, obviously. We gave priority to Map Italy acquisition because in this case, change of direction is more reliable because we have the same geometry of acquisition. In case of unavailability of Map Italy acquisition, we gave priority to acquisition with low look angles because acquisition at high look angles are disturbed by, let's say, vertical structures like walls and trees, even if, as underlined before, we are not able to see inside urban areas and we are not able to detect vegetation under water under dense vegetation. So when 2 images were needed to cover the area of interest, we gave priority to acquisition along the same orbit. So both ascending or both descending. We avoided mixing ascending and descending orbits. And for instance, this is an example, May 17, 1 Map Italy image acquired at an incidence look angle of 24 degrees, and another image acquired at the high incidence angle. But this was the only opportunity that we had. The following days, again, we had another Map Italy image, and in this case, to observe this area, the Italian Space Agency was forced to turn the look angle, the look side in the left direction and again observe at quite high incidence angle. So this is just an example, and this is our set of flood images from May 17 to May 21. Again, right ascending, and very different incidence angle, and only 2 mappable images. From May 22 to May 26, again, the same story, and only 2 mappable images, only 2 interferometric images. And finally, from May 27 to June 3, again, only 1 mappable image. And as you can see, we have a look angle of more than 50 degrees. So it is quite, it is a problem when applying change detection. So the pre-processing of the SAR images, multi-lacking, geocoding with 5-meter resolution then provided by the Emilia-Romagna region, calibration, obviously, the speckle filtering, the gamma filter, and then one aspect that I missed to underline. Okay, look at this. They are stretched in the same way, but you can see that there is a miscalibration. This is a problem, especially between Cosmos Skymet first and second generation. So to at least partially deal with this problem, okay, we apply the simple linear scaling. And again, we apply the square cosine correction to account for the different look angles, except obviously for interferometric pairs. In this case, we do not have this kind of problem. So this is the processing. How did we select the pre-flood images? When interferometric pairs were unavailable for each flood images, the pre-flood images was selected based on same orbit, either ascending or descending, maximum coverage of the area covered by the flood image, similarity between the look angles, and if, as I showed before, 2 images were required to cover the area of interest, in the overlap area, we gave priority, which shows the image with the incidence angle more similar to that of the flood image. So, for instance, this is a flood image acquired on May 25, and these are the 2 pre-flood images used to perform change detection. So this is what we got. It is a false color composition. In red, the pre-flood image, and green and blue, the flood image. This is not ideal, again, because the incidence angles are different, but this is the best we can do if we want to apply change detection. As you might see, there is a small area that is not covered by the pre-flood image, but it is outside the area of interest. For what concerns the flood mapping, we applied a fully automated algorithm because we do not want to rely on the skill of the operators. We want to do something that anybody can run. So the steps are a preliminary clustering of the post-flood image and the different image, the intersection between the clusters with the low median value of the best scattering, the sigma 0 post, and the low and mid value of the difference image. And to find the threshold dividing flooded and non-flooded area, to do something that could be fast, we focused on the area that are likely in the boundary between land and water. So we applied an edge detection at the output of the ISO data. We performed a buffering around the edge, and then we apply the OTSU thresholding, automatic thresholding, just focusing on the pixel in a buffer to speed up the process. And finally, to account for the spatial context and account for the uncertainty of the threshold that was underlined before, we applied also a region growing algorithm. And just to show you in detail, this is an example of a post-flood image. This is the output of the clustering. This is, again, a combination including pre-flood and flood images, the clustering of the different image, the intersection between the clusters, the edge filtering, the buffer around the edges. We trying to find the threshold in a fully automatic way. And finally, this is the flood map. So after all this processing, that again is not the best we can do, but we are in a condition where we are required to observe continuously, persistently an area. This is what we got. This is an animation that illustrates the evolution of the flood from May 70 to May 31. Okay, again. Okay, I'm not much. And we were also able to produce the water depth maps using the FW depth algorithm, and again, a digital elevation model provided out by Emilia-Romagna region. And unfortunately, we had to repeat the same exercise 3 weeks ago because Italy was hit by another big flood in Tuscany near Florence. And again, 9 people unfortunately were killed. 1,200 people were displaced. This is in red. You can see the area of interest. This is a photo of one of the flooded areas. And again, this is what we obtained. And also in this case, we produced the water depth maps. In this case, I just show you 2 zooms into flooded areas. So the conclusion, okay, Cosmos Skymet and Cosmos Skymet second generation are suitable when the persistent flood monitoring is required because of their on-demand capability. We process all the data with a fully automated algorithm, and as underlined before, we cared about validation. The only reference data we had is a Sentinel-2 image acquired on May 23. This is the only Sentinel-2 images with no cloud cover or few cloud cover. As underlined before, I don't want to stress these results because they are in some way misleading, because again, we are not able to look at flooded areas in urban floods in urban areas. It can be done with other processing that implies interferometry or looking at the double bounce, but it is quite consuming, and sometimes it works and sometimes it doesn't work. And moreover, we are not able to see water under dense vegetation, and we also mask this areas with complex topography, slopes larger than 7 degrees. Just to, let's say, deal with the different viewing geometry, we also perform a processing based on simple consideration. Pixel flooded at time t0 and time t2 should be classified as flooded at time t1, and vice versa. Also, but this kind of exercise implies a delay in providing the flood map, because we have to wait for another day. The outlook for daily monitoring, obviously, we need a sensor able to perform last-minute planning, or at least the acquisition request sent as late as most late as possible, near real-time data delivery, and on-demand data coverage. We, and it is a key point, agreed the acquisition plans with either with both the flood managers and the Italian Space Agency. So it was an agreement. And we also, a recommendation is the maximum automation of the processing for a fast delivery and for objectivity and traceability. So the exercise can be repeated as many times as we want. And finally, for the future, at least for Italy, there is the constellation, that is a constellation of constellations funded by the European Space Agency and the Italian Space Agency that will include also X-band served data with hopefully daily revisit. So that's all. Hope to be in time.
Yeah, perfect.
I suggest we hold questions until the discussion session because we need to move on right away. But but please save your questions for in 18 minutes.
So I was not in time.
Yeah,
But-
you were perfect in time.
Ah, okay.
The thing is, you have no time for questions now.
Thank you, thank you. All right, let's thank the speaker again. And last but not least, we have Paul Beckham.
Hi, everyone. My name is Paul Gerabetcom, and I'm happy to share to you this study on Lake Tanganyika total water storage for water balance monitoring and flow study. We made this study in Lagos with my colleague of the Jet and Hydromatter. And concerning the background of the study, as most of you know now, in the 3 or 4 last year in the region of East Africa, there were an increasing of rainfall. And the consequence was the strongly increase of surface water level for many of the Great Lakes in this region. You can see that compared to the level in 2018, some lake like Lake Kyoga raised for more than 4 meters, and lake like Lake Albert and Lake Rukwa raised from more than 3 meters. And you have lake like Turkana and Victoria that raised for more than 2 meters. Some country in this region also face on floods. You can see the floods in countries like Uganda, Somalia, Ethiopia, and Kenya. And some organizations in this region report the flooding, the death of more than 500 persons, and also the loss of more than 2,000 animals in this region. On our area of interest, the Lake Tanganyika, floods affect more than 300,000 of people, and in the Democratic Republic of Congo, and also more than 50,000 of people in the Burundi Republic. We can also see the rising of Lake Tanganyika for more than 2 meters compared to the surface water level of the lake in 2018. And we also have the consequence of rainfall in the shore of the Lake Tanganyika. And we also have the population who have been displaced due to this to flood in this region. So based on this background, our objective here was to study the effect of climate change on total water storage in the Lake Tanganyika watershed here. And for this, we calculate the water budget on the watershed, and we also calculate the water content in the different reservoirs inside the watershed. And the second objective was the mapping of flooding in the region, and also to try to estimate the flooding in this region. So for this, we start by calculating the total water storage variation using GRACE data. And also we calculate the water budget inside the watershed. And for this, we use rainfall data, discharge, evaporation and evapotranspiration, And we start by making the difference between water budget in the lake from the water budget in the rest of the watershed. So for the water budget in the lake, we use rainfall, discharge, and evaporation. And for the rest of the watershed, we only use rainfall and evapotranspiration. As we have a lot of data of evaporation and evapotranspiration, we divide this data into two groups. In the first group, we extract evaporation and evapotranspiration from ERA5 land data, and we use global lake evaporation data for evaporation of the lake, and MODIS data for evapotranspiration of the lake. And as we had 5 data set of rainfall, we calculate the water budget for each rainfall data set. So we have 2 results. The first result is for each rainfall obtained with evaporation and evapotranspiration for ERA5, and the second result are obtained with evaporation for global lake evaporation volume dataset and the MODIS dataset. So after this, we also calculate the water volume in the different reservoirs inside the watershed by using total variation of total water storage with surface soil moisture and lake surface water level. And then we calculate, we also make the fluid mapping inside the region by using Sentinel-2 data. We also complete this analysis by making the space-time variation of rainfall inside the watershed, and we also use total water storage variation with lake water surface to calculate the correlation and also try to estimate the floods in this region. So as first result, we have the water budget in this watershed. In the left column, you have all the 5 data sets we use. In this column, we combine our 5 data set with evaporation of global lake evaporation volume data set and MODIS evapotranspiration. And in the right column, you have the combination of 5 data set with evaporation and evapotranspiration from ERA5. For each plot, in blue, you have the variation of water budget inside the lake. In orange, you have the variation of water budget in the rest of the watershed. And the sum of the both variation is supposed to represent the budget that we represent here in purple. And for each plot also, you have the variation of total water storage inside the watershed. We can see that among all this combination, there is only one combination can help us to close the water budget in this watershed. It's the combination of precipitation from ERA5 and evaporation of glaive data and evapotranspiration from MODIS. And we can see an increasing trend of total water storage inside the watershed, also an increasing trend of water volume in the rest of the watershed, and a decreasing trend of water volume inside the lake. So we assume that we think that is an underestimation of rainfall in this specific region by the other rainfall dataset, and also the underestimation of evapotranspiration from ERA5, which the cause of the result from the other combination. As second result, we have the water contained inside the different reservoir. We can see that total water storage in this reservoir is composed by about 90% of groundwater, 8% of surface water storage, surface soil moisture water storage, and less than 8% for surface water storage, and less than 2% for surface soil moisture. We also compute the seasonality of this variable, and we can see that the maximum of total water storage and groundwater are obtained in April, when the maximum of surface water storage are obtained in May. So there is a 1 month delay of surface water storage in response to variation of total water storage. And we also had a correlation of 90% between surface water storage variation and total water storage variation. So this 1 month delay and the correlation, we will use it for estimation of a flood in this region. So before it, we tried to understand the variation of total water storage we had. So to do it, we calculate the space-time variation of rainfall, evapotranspiration, and evaporation in the whole watershed. We start by rainfall. We divide the signal of rainfall between seasonality and trends. And we found that inside the watershed, 97% of rainfall are recorded between January to May in the given year, and also between October to December, with maximum registered in December. And for trend, we found that an increasing trend of rainfall inside the watershed, and these increasing trends are very particular in the Malagasy basin. So for the trend inside the lake and in the rest of the watershed, you have here the trend of rainfall and evaporation inside the lake. We can see that rainfall remains stable, evaporation remains stable when rainfall are increasing. In the rest of the watershed, you have an increasing trend of evaporation and evapotranspiration. But between 2003 and 2005, value of evapotranspiration are biggest than the value of evaporation of rainfall. Is one of reason why we have a decreasing trend of total water storage in this between this year. So now concerning flooding, to study flooding, we download Sentinel-2 data from 2016 to 2022, and we only make the flood map in the northern shore of the lake because it's the most urbanized zone, and you also have a natural reserve here. So between 2016 to 2022, we try to download all available Sentinel-2 data in this zone, and we apply a MNDWI index to extract the flood area in this area. We have here the time series of flood area. So there are a lot of data because some images was covered by cloud, so we cannot have all data, all Sentinel-2 data in this period. But when we can also see that you have an increasing trend of flood area from the end of 2019. And when we calculate the seasonality of this flood based on this time series, we see also that floods were maximum in May. And we remember that May is the period when surface water storage is also maximum in this area. So we have here the mapping of floods in the May during this period, and we can see an increasing trend of flood in the wetland. We also have an increasing trend of flood in the urban area, and a recession of the coastline in this area. So after this, we try to estimate the floods in this area. We use the highest correlation between total water storage and surface water storage, and we also use the 1 month delay of surface water storage to total water storage. So we calculate the correlation between May surface water storage and April total water storage and found a correlation of 97%. And we also try to extend this estimation by using total water storage of March and also total water storage of February. But to calculate this correlation, we only use value from 2003 to 2020. So we didn't use the 2 last year value when flood were very highest to try to estimate flood and compare to the observed value. So this is the correlation. And here you have the estimate surface water storage based on total water storage of April, March, and February. And you also here you have the observed value of surface water storage and of May in 2001 and 2022, and 2021 and 2022. And you have the estimated value here. In 2001, the best value are obtained with total water storage of April, and in 2022, the best value are obtained with total water storage of March. So we explain this difference by the fact that during 2003 and 2020, we first have like a missing value here, and we don't have a very important variation. So we think that using if you extend our observation period, we can improve this estimation. So as conclusion, we show in this study that evapotranspiration and rainfall are the main driving factor of total water storage change in the Lake Tanganyika watershed. We also see that rainfall increase were very highest in the Malagarasi basin. And we also see the increasing trend of total water storage in the study. And now we think that as perspective, we think that investigating other parameters like land surface temperature or maybe vegetation cover or agricultural spray can provide more explanation of the variation of total water storage we highlight in this study. We also see the increasing floods of wetland and urban area and a recession of the coastline in the northern shore of the Lake Tanganyika. And we think that it would be very important to study the impact of this increasing flood in the wildlife, especially in the natural reserve called Ruzizi Nature Delta Reserve. And finally, we also see that total water storage can be used as an early warning of flooding in this area. But we also know that the estimation that we use in this study can be improved by using a lot of data and to improve the correlation and the estimation. So thank you for your attention.
Perfect in timing as well. You guys make it so easy to have the 20-minute, even 25 minutes now. And you're lucky because you get to start the discussion. So are there any questions for this particular talk? Because we've got about 3 minutes left.
Thank you for your talk. Very nice. I really like the idea of using terrestrial water storage to predict surface water formation. I think it's brilliant. And the time series you showed of soil moisture have really, really small variability, even though there's big variability in surface water. Did I understand that correctly?
Is that the variability of soil moisture is less than the
Very small? Is it, did I, if I understood correctly, it looked like in the plots that the variability of soil moisture is very small and the variability of surface water is very big.
Yes, because soil moisture compared to the other variable is very small. We only use the first centimeter, so it's the surface soil moisture. So the amount is not is very less than the amount of the other variable.
Okay.
But if you make a plot with only surface soil moisture, you will have the variation.
Yeah. Okay.
But compared to other variable, is very.
Okay.
It's very.
So probably some subjectivity in the definition of soil moisture and groundwater and how to partition those two variables, right? Okay.
Yes.
Thank you. Right. The remotely sensed soil moisture is only those top few centimeters, yeah? Yeah. 5 centimeters, yeah. Yeah. Okay. Thank you.
Any other questions for Paul Gérard? Go ahead.
Sorry. I have a quick question. So that suggestion at the end, I liked it as well, that I'm not into total water storage, but I think it's a great suggestion to link it to as a predictor for possible flooding. How confident are you? Have you made some trials with this, or is this, is this the next step, or have you made some trials and you have some initial results on this?
It's the next step because you want to generalize this study in the region, and we need, yes, when we will generalize, we will make the validation and know if total water storage is very
Great. Thank you.
significant for this estimation.
Great.
I think we can thank our speaker and get started.
We are actually finishing the talks 10 seconds after 3:40. This is something to go in the history books.
I promised. So this is going back to quality of flood maps. So in ISI, we have been having the chance to observe floods every few hours, right? Like similar to what Cosmos Sky showed, like every 4 to 6 hours, you see. And then what is blowing our minds is that it's so hard to validate the accuracy of those maps because you don't find better data. So I think the temporal dimension is a challenge that I think we need to address and bring to the community as well. So you have a flood mask, most of the times they are from Sentinel, but that could be a 6 days timestamp of the flood. We have long duration floods. And then I think that's a challenge that we are facing seriously, how to validate the temporal dimension of those maps. The answer might be in hydro models. I don't know, maybe just to provoke that thought.
Thank you. Sorry I cut you off earlier. That was a great comment.
So I think the bunch of presentations was really nice. It was really nice to see some of the discussion about the validation, but I did have a couple of thoughts on that. I think most of the stuff that I saw was they were trying to equate false alarms with misdetections, but there needs to be a thought about the impact of false alarms and the impact of false detections. Is the impact the same? I don't think so. There's a bigger impact of a misdetection than a false alarm. So that needs to be considered when you decide where threshold is of your flooding map, because agencies are going to be using that flooding map. And then if you have a misdetection, that becomes a bigger impact. So I would suggest one of the communities which is there in earth science, which has widely been using this false alarm misdetection concept, is the precipitation community. And they have a fairly robust protocol that they have developed over the years. And then maybe some of the stuff can be borrowed from that in terms of protocol.
Yes. I just add to that. I agree, because in hydrology, we already sit in the WMO for guidelines on measuring rivers. I think it's very smart to also go with the atmospheric or meteorological community again in hydrology for this, because we already go in hydrology with WMO anyway, which is meteorology. So thank you very much for that. Yeah, it's a bit of a backing.
Yeah, did you want to comment?
Right, so maybe like 2 comments. First, on the temporal stability, this is very, very important. And you're right, hydraulic models do provide a possible solution. But something that we've been, so for instance, some years ago, a team at the Luxembourg Institute of Science and Technology, they showed that a bunch of the contribution of the floodwater came from groundwater. When I say a bunch, it was over 50%. And this means that if your model is not capturing this process, you will not capture this water. So you will end up falsely penalizing your map. So it works, but not all the time. So either we develop a model that is able to capture every single flood process and you supply it with the best data possible for the temporal sampling. Otherwise, what is also possible to look at are insurance claims, but that is obviously later. It's possible to look at citizen science data, which provides on-ground photos often. It's also possible to look at newspaper articles where you can also find locations. These are not exact, but they do provide a data set to assess stability in time that is independent of process representation. This is important. And maybe to come back to the precipitation question, this is a super idea. Thank you, Rajat. But maybe just to play the devil's advocate here, when we misdetect multiple times, right? So you said basically that the impact of false alarms is always maybe less than misdetections, but I slightly disagree, because what we are also trying to do is build trust And in this case, so there's trust for two things. One is also for emergency management applications such as evacuations for flooding. So when you have large false alarms, you ask someone to move, they move the first time, second time they will not move. And so when we think about impacts of things like emergency management, it's not just the mapping exercise where we make some maps and okay, type 1 errors are better than type 2 errors. It's really not that. It has to be a balanced assessment because we need to build trust in our products.
I agree with the trust part, but the only comment I would have is a misdetection would lead to a loss of life, whereas a false alarm would lead to a mistrust.
Please.
No, you have to understand, of course, we're working in an emergency context. In this case, people need information. We are working with professionals, okay? These men know how to deal with a certain level of uncertainty. And once I said to a fireman, I said, you need to use a map. He said, don't worry, we will never forget someone on the field.
Regarding the problem of, let's say, misdetection, I can talk about my experience with the Italian Department of Civil Protection. They are perfectly aware that we are not able, except for some situation, to observe floods in urban areas that are the most affected area from the point of view of the impact. But I was told we know because there are, let's say, people that takes a picture with his mobile phone and so on. So we almost know the urban areas that are hit by at least, I can talk about Italy, probably in remote regions, the problem is, the problems you mentioned is more critical, but at least in Italy, they are perfectly aware that misdetection are possible because there is a sort of limit of SAR, or also of optical data. So they are perfectly aware. We provide them with the best we can do, but they are perfectly aware that, that is not the ideal situation, that we are not able to map with big precision the flooded areas, so, at least from my experience.
So can I?
You can. I'm just holding the mic.
Back to Luca, because I have a question for you, Luca. It's a very interesting one, but it's a bit different. But it goes back to what I said yesterday, bringing the user back in, but a different user, maybe thinking very differently. So in Emilia-Romagna, the floods you showed, there was a very interesting moment when Formula One cancelled the Grand Prix because of the floods.
Yeah.
And officially, they said they talked to Italian rescue, and they said they didn't want to pull rescue people away to go into the Formula One when there's the floods going on. But there was also a mention about they were worried about safety on the track. Now I know tarmac is very, very hard to detect, wet tarmac versus dry tarmac, but because you're the expert and also with Cosmos SkyMat, have you ever tried doing water detection on surfaces like that, or maybe using what I've just said to maybe try to go to Formula One and say there's an interest in this region because we are seeing more floods there? How about I'm not saying they should pay for something you do, Formula One, but it is a very interesting, to me, it's a very interesting angle that, this, because there's a lot of money being lost, I guess, if you start switching dates on when you hold Formula One because of rainfall and flooding. So do you have any thoughts on that?
Unfortunately, not. Most of the times when we were activated by the Italian Civil Protection, we ask for feedbacks from the regions, but usually we don't have. I don't know why. Probably in Italy, this is a problem of competencies. For instance, I work with also burned area mapping, and burned areas, the competency is regional. So for flood mapping, the competency is national. So it's quite different. But Emilia-Romagna is a challenging area because we had big flood also in 2014. Probably you remember we And so, but unfortunately, we did not have any feedback also about the reliability of what we provide.
Yes.
We unfortunately no. This is the problem related also to the validation. So this is unfortunately we didn't.
Yes.
Yeah, I have a couple questions regarding the Cosmos Skymet presentation, which I think is a nice example of what you can do with rapid revisits, high resolution SAR constellation. I was wondering if you could give a bit more details about your collection strategy. Like, do you get your area of interest from maybe the civil protection agency, and do you know what kind of inputs goes into that area of interest? Do you look at just rainfall, or do you have some kind of hydrological model to have some expected flood footprint? And second question, I understood that you mostly collect strip images during your activations. Have you ever evaluated using a spotlight images, maybe in urban areas where it's a bit like some improvements or something like that? Thank you.
That was a question for Luca.
Okay, regarding the first question, this is one of the most critical points. Probably it deals with the tasking in anticipation. The problem is, for instance, I showed you the flood in Tuscany. In Tuscany, we have a red alert in Veneto. There is a region in northern Italy. And then the flood occurred in Tuscany. So, and moreover, the area where there is an alert usually are quite wide. So the tasking of the satellites in wide areas risks to be a sort, you have to say, let's say lucky, if I can say, use the term lucky in such a situation, to observe the flood when you have tasking anticipation. So usually what we are forced to do is to wait for at least an hydrometer that issues an alert. Okay, the water is or the water level has exceeded an alert level. So in this case, we become to task the satellites. But based on just meteorological forecast or flood modeling, the risk is of, let's say, false alarm. For what concerns your second question, the problem of the spotlight is that is say a spot acquisition, so we do not have any pre-flood image. So sometimes because of let's say shadows and so on, also looking in urban areas could be misleading. So I'm afraid we are not able to provide a reliable score. And moreover, if we acquire the acquisition are in conflict. So if we acquire a spotlight image, we are not able to acquire a street map image and vice versa. So this is the problem.
I'm going to move to this side of the room to make sure that we have a center of gravity in the questions over here. Anybody? What are your thoughts on water science and society? Questions? Yeah.
Yes, well, maybe after all the talks, I think it's evident that we still struggle with finding water below vegetation. So we've seen that, for instance, some modes work, some work don't work depending on the mission. So I would say that looking at water that it's not covered by vegetation, it's an anthropocentric point of view, right? Because we're worried about the flood in the cities, in the agricultural areas. But from a more ecological perspective, it will be interesting to see plot mapping below vegetation and seeing how is that affecting, for instance, wetlands or coastal plains. So maybe, yeah, maybe a little bit of a food for thought on that. Like, yeah.
Thank you. Let's make sure we capture that in the notes. Do you have any thoughts, Laetitia? You sure? Anybody else?
Yeah, over there. I go after.
Okay, thank you. Nuno Moreira from the Portuguese Met Service. So I would like just to give an idea here on the on missing or not missing and being over. I think we have, of course, connection also with the civil protection. on a national level, sometimes on a regional level. The thing is that I think we get more complaints in commas, of course, if we miss rather than we do more and we do extra. So clearly that's our perspective. We don't have the civil protection here to say, but of course it should be different. You agree? It should be. It can be different in different countries because maybe the connection is different. It's not the same everywhere, so there might be some differences. But I believe that as they are experienced users working together with us, the providers of information, they are used to know that sometimes we miss and sometimes we do a warning for a large area, and they know that's not going to happen in that area. It's going to be in a small part. And even at the regional level, I already have the feedback that they know that if I warn for Lisbon, it's not the Lisbon district, it's not all Lisbon that will be necessarily affected, and they know that some small counties will have and some others will not. So I understand your concern about being crying wolf, crying wolf, crying wolf, and then nothing happens. I think that can happen more with inexperienced people. So the general public I think the general public can relate more to that, but the experienced civil protection people, I don't think they do. So of course there is a problem because people are the ones that have to react to civil protection actions or orders. But in the end, civil protection and the authorities that are led by civil protection, somehow they act. And then they make people move if necessary, even by force in the limit. So in the end, in the balance, I think it's better we don't miss. Yes. Yes, and they know when it's completely out of forecast.
Thank you. Hey, we've had a lot of conversation about detecting when we have a satellite at the right time in the right place. I was wondering if we had opinions on forecasting, perhaps from some of the modelers in the room. I see 3 at least. Oh, yeah.
Yes, the product, as Adrien presented, you want to test a forecast product. We also do some kind of hydrological model with observed data, but also with forecast data, and it's clearly a big issue because already the observed data are not very accurate, above all to make a flood prediction, and perhaps it's better for drought, but so it's a big issue for us. It's a daily issue to have a good forecast quality data, but of course, so it's always difficult to present this result, but we do it, as we say, because we don't want to miss an event, but we have to be very aware of the big uncertainty for the forecast product nowadays, perhaps. In the rain, I was speaking about the product of forecast. Yes, of course, it could have also uncertainty on the model.
JT.
I would just make an argument for probabilistic approaches instead of very highly deterministic things, right? Saying like, well, the risk of this happening is this. And so using validation as a way to develop probabilistic approaches, I think might be the most intelligent way forward. I mean, of all of the operational agencies that we've worked with at NASA in the United States, you know, remote sensing products or models are not the only point of information that they're making decisions on. They have a portfolio of information that they make decisions on. And if satellite data are one point in that portfolio, it's still valuable to them. But they weigh that maybe in the face of other things. And so offering not only, oh, this is going to flood, or there's going to be a fire here, or there's going to be a drought here, but saying, we believe with this confidence that somewhere in this region, that sometimes is still actionable, because then they have other tools that can help refine that piece of information.
Very good. Actually, in my invited commentary, the second section is where did uncertainty go in the flood mapping? But we don't do it anymore. We used to do it in like late 90s, early 2000s was a huge community in remote sensing flood mapping. Now it's funny that a Grace person tells us how to do the flood mapping correctly, because I think that is a very good point, JT. Thank you so much.
In the same direction as what was just said, and also I remember yesterday or 2 days ago, somebody said that he was not very optimistic about the fact that remote sensing could help for flash flood or this type of stuff. But also it depends on how we use this type of information. And I don't work on flood prediction, but if I take an example of what is done in France, for example, there is this company. Every time there is a flood in France, you see the Predict. They go on TV and they explain. In fact, the way Predict, it's a company, is working, and you know him quite well because the guy was from VRL. In fact, they use maps, so they have some contracts with cities, and some very small cities, so impacted by flash floods, and they don't use satellite information in real time because it's not adapted to the problem. But they have maps of the city and where you can, depending on the events, where it can be dangerous, where you have to move people, and so they use indirectly or offline satellite information to set these maps, for example. And then in real time, of course, they don't wait for Sentinel something to be somewhere close to the city. But so it's also a way to use satellite information, but in a way adapted to the problem. So it's still using satellite information, but maybe not the way as not using model real time. And so you have a portfolio of ways to solve a problem, even in emergency situations, but then adapted to the situation.
You want to? Yeah.
Just to go in the same way, for example, we will develop a flood alert in Abidjan, and we will propose. We don't know right now if we will propose a portfolio of predetermined flooded area or flooded area in a near real time. We will see, because it will be the study and the ongoing process. We will make us to decide what is the best for the uncertainty.
You guys, we did very good. I see we have a couple more points, so let's make sure we have comments, and then I want to make sure that everybody have coffee also.
I'm Pedro. I'm from Hydrospace here from Lisbon. We work with modeling. The experience we have with modeling flood areas is that it's always a question of time and space and the detail that you have on time and space. And we in the models, we can have all the detail of the world, and in time and space, we can do whatever we want. Normally the bottleneck is how good our data is. And normally we say if we have a very detailed topography, we can model any flood. If we have a good rain, of course, also. So the idea I have that the concept of the digital twins, and to be able, for us to progress a little bit, I would say this is the idea of this Congress, for us to be able to progress a little bit, I would say that it will be very important somehow to find ways of more and more having databases with all this data that we can take the advantage of all the different aspects. So the modeling, we can go for all the detail, but we are dependent on having good inputs that can come from space eventually, very detailed topography, for example. But we can also provide, and now we can see if we want to validate the models with the flood that we manage, with that we measure from the sky, or if we want to validate the flood that we manage from the sky with the models. Eventually we can do it both ways. But in the end, my message is just that if we find ways to learn with and get this information all together somewhere, we'll be able to progress a little bit more.
because I would say that both space and models have win-win situations where one can improve the other. And I think that now we are in the sweet spot where all these satellites going up, we can define what will be the important things for us to choose, to improve. And yeah, that's, thank you.
Do you want to take us home?
I have more an open question. I'm Santiago Peña from CNES. And it's, I don't know, since here we have in the room some people working in emergency plans and doing emergency maps for flooding, how the new space or new companies for radar, like Capella, Umbra, or ESA maps, are they used? Are they providing something new? I don't know, I'm just curious about the new situation because they are providing like quite cheap radar information, but maybe not as good as Cosmos SkyMed or whatever. So this is a question for maybe Luca or Hervé. No comment? No. They're not good? No good data? I'm curious, I don't know. Yeah.
My experience in the protection does not want to work with commercial data in general. So this is because they, let's say they pay, or Italy and other areas pay Copernicus. So in case they ask to the Copernicus Emergency Service to acquire data belonging to their portfolio, and for instance, in urban areas, if there are cloud-free images, they task, let's say, WorldView rather than Pleiad or Spot. So this is my experience. Regarding, generally speaking, regarding the problem of the timeline, as obviously ESA, Capella are very promising. I do not have any experience, honestly, with this kind of data, but I suppose they are.
Concerning ISAT, I can make a small smart comment. In fact, we work within the framework of rapid mapping services for Copernicus, also with some framework with the CNES, and also with a bilateral agreement with a local water agency. And for this last one, we have to react on demand. So we have already have a bilateral agreement with RadarSat, Cosmos SkyMed, TerraSat, for example. ISI never want such. They want all the market, from the image to the products. That's the first one. So we cannot evaluate the data. The second point, we were not also able to evaluate their products. They met a lot of pressure towards the Commission to get the contract, to say that what OMS is doing is bad. We do much more better. But I never see any benchmark of product. So I can't say more.
Okay, let me just conclude by saying thank you to whoever set the temperature very low over here, because nobody fell asleep and I've seen a lot of people freezing. I suggest we go warm up with coffee. If you have more thoughts on data products, share it with your colleagues over there, and give yourselves a round of applause for the contribution.
First presentation is from Francesca Vanzi of Human Research Foundation with the presentation with the title Developing Snow Drought Indices Using HSAF Operational Products.
All right. So thank you. Where is it? Okay. So thank you for being here. The presentation that I'm going to show to you today is, as Simone mentioned, is about the use of HSAF operational products, so the EUMETSAT suite for support to hydrology, to develop indices to characterize snow droughts. Before we go into the details, just a few information on why we focus on snow droughts in particular, because they are occurring more and more frequently over the last few years. This is an example for Italy in particular is an estimation of the deficit in snow watcher equivalent for April 2023. As you see across the board, we have red conditions, so a negative anomaly of snow watcher equivalent across all of the Italian peninsula. And this is not only for Italy, of course, this is an estimation of snow watcher equivalent for the Swiss Alps made by the Swiss SLF. You see a similar conditions. So 2023 low snow watcher equivalent compared to the average during the historical period. So obviously, what we see is a need to address what are condition of snow deficit in not only in terms of snow covered area, but also in terms of snow watcher equivalent. I cannot see the slide very well, but anyway. Obviously, it's not only a problem for snow, it also becomes a problem for water supply in general. What you see here, for example, are various river sections across the Italian territory. The more red, the more snow is important in terms of local water supply. Is an estimation that we got again using national data. You see that there are areas of the country where more than half of the water supply likely comes from snow during the winter. So in situations like this, obviously Italy is just an example. In situations like this in general, a deficit of snow during winter will then be a deficit of water during spring and summer. Christian this morning was mentioning how important snowmelt is for irrigation. We get 70 to 80% of our irrigation water supply from surface water, so basically from snow. And these are examples of the total amount of water at the closure section of the Po River Basin. Is a paper by Montanari and others. You see 2022 here, the lowest year from during the last 2 centuries. Also, the year with the record low snow watcher equivalent during winter. So again, you see the association here between low snow watcher equivalent during winter and low summer flow. So if you are a snow hydrologist like me, your winter tend to be pretty busy with questions like this one. You come across decision makers of any kind asking you to predict water supply for the next 1,000 years based on a random amount of snow they have measured at a specific location somewhere in the world. So here again, even if we tend to work during winter, the implications of what we do stretch well over spring and summer. So to support this poor guy who has to go through these questions, what we're trying to do is to develop snow drought indices based on satellite data of snow. We are doing this using the HSAF suite, the suite of operational satellite products by EUMETSAT, developed specifically for hydrology. These are operational, historical data sets of precipitation, snow watcher equivalent, well, snow in general, and soil moisture. We have seen some examples this morning by Mariette in particular. And what we show here are similar applications using the snow products. HSAF provides, in terms of snow, data of snow covered area, fractional snow cover, snow watcher equivalent, and snow wetness in particular. We are using 2 data sets in particular. One is the snow covered area by Severi. It's the H10 product. I'm not a developer, so don't ask me specific question about the satellite data in particular, but these are daily operational products delivered by HSAF freely to anybody. You see an example here of snow covered area for November the 8th. And you see very well the development of the snow covered area across the European Alps in particular. So again, these are freely available, validated. We validate them every year. And if you're interested, you can obviously get access to them. Another data set that we use is the fractional snow cover. H12. Again, this is also daily. It's based on a data fusion of different sensors, and it provides 5 to 10 kilometer resolution data of fractional snow cover across all mountain chains of Europe and nearby areas. There are also other products with hemispheric coverage, and we will go into that later. So what we did, we developed an operational chain which downloads this data automatically every day, computes anomalies compared to the climatology, and deliver decision-relevant plots of these anomalies compared to the historical period, which for HSAF is quite short. We go from 2012 roughly to now, but of course this data set is growing every year that passes. This is an example of a previous work that I just wanted to show, to acknowledge that the work that we are doing is in continuation with some work that our colleagues at HSAF have done in the past. What you see here is an anomaly in terms of snow covered area for 2023. You see again very well how dramatically the anomaly was for the Italian Alps in particular, with, on the other hand, a positive anomaly across the northern side of the European chain. And this is generally the synoptic condition we tend to encounter. We either have positive anomaly on the southern side or on the northern side, and vice versa. So the example of the plots that we deliver every day, this is an example for the European Alps. You see the black line is the historical mean day by day of snow covered area across the whole of the Alps. So from France to Slovenia to the northern part and so forth. The red line is, on the other hand, 2022, 2023. And again, what you see a spike in snow covered area during regional snowfalls, but then during 2023, a decline that led to conditions that were below average conditions, both in January and then again in March and May. So this is an example for the European Alps. We have similar results for the Pyrenees, for example. Again, same story, quite average conditions at some point in February and March, and then a very quick snow melt and decline of the snow cover across the board, across the whole of the Pyrenees. Another example again, Turkey. In this case, we had a different dynamic. Very low snow up to March, and then a spike and back to average conditions. So we are able to monitor these situations from the Pyrenees to Turkey to all the other mountain groups of Europe and nearby regions. We are also delivering anomalies of fractional snow cover. Pretty complicated plots, I have to say, to analyze. It's probably less straightforward when you look at fractional snow cover than snow covered area, but we deliver such maps for the all of the European continent every day automatically. And we are now discussing how to disseminate these results on media, on social media and the like. Next step in terms of outlook, HSAP, as I said, also provides hemispheric and geostationary snapshots. The data that we use originally, the H10 product I was mentioning, covers this area, but obviously it also offers other areas, for example, the Northern African part and so forth. And then when you look at other products like H32 and H35, you get snow-covered area for the all of the mountain regions of the world, with particular reference for the Northern Hemisphere, of course. So our next step in this case is to go global and so deliver similar anomalies for all mountain chains of the world. So in terms of recommendations, as I said, I think I tried to deliver the message that snow And snow products, when you look at satellites, are not only winter stuff. We need to know how much snow is up in the mountains to plan water resources management accordingly during summer. And so the work that we do is really has more to do with spring and summer than what you might expect. Obviously, high resolution is very important. We also saw a couple of presentation about that yesterday, and we are very happy to see advances in that regard. But don't forget that decision makers sometimes want the synoptic view. They want to see things across the board. To think about Europe, across the large mountain chain of the Alps, and we are often asked, okay, we are in this situation, but what about our neighbors on the other side? So we need both things, both high resolution local information, but also synoptic. And the third, there is obviously a long history of snow-covered area missions, which are very helpful. All the anomalies that I showed here are in terms of snow-covered area. But SWE, as Noah Moloch said yesterday, is the holy grail of snow hydrology, is where we want to go, also in terms of snow mission. And to convince you of that, these are a very good example of last year, more or less April. It's a different product. It's based on other satellites, but it's a product that we deliver together with ARPA Valle d'Aosta to the Aosta Regional Administration. What you see here is a similar plot, the one that I showed to you, but only for Aosta Valley, in terms of snow-covered area and in terms of SWE. If you look at snow-covered area, you might conclude we are in an average year. But then if you look at how deep the snow is, you see very well that it was far from being an average year. So that's why we think snow-covered area is good, but what we need to make decisions in the end is snow watcher equivalent. An example of that, we are right now assimilating Sentinel data and HSAF data importantly in one of these modeling chains. We think that at this point, the most mature way of getting this SWE estimate is really to blend and assimilate this data into operational snow model. For Italy in particular, we have this chain, many other agencies and many other contexts have similar SWE monitoring chains. Again, as a snow hydrologist, there is a high, let's say, history and tradition on snow-covered area, but what we need to help this guy again is snow watcher equivalent. Thank you.
Sorry, maybe I missed that. HSAF is, why do you send final stuff now?
It's true. So we have it's called H13. The point is that it is was developed like many other SWE products for flat Arctic regions. So in those situations, it worked very well because snow is dry, it's shallow, and obviously in those contexts it's very useful. But when you go to the very complex terrain of the mountain regions, then at the moment it's very hard to use. I think it's 10 by 10 kilometer or even more resolution for that.
The next question, when is your product?
So that product is the result of an operational chain that we develop and maintain for the Civil Protection Department in Italy. The historical data are available. We published a paper and we maintain it every year with some latency. The real-time data are not available unless you are part of the constellation of civil protection agency in the country. But yeah, we are obviously available to share for research purposes very, very easily.
Any other question? So thank you, Francesco.
Thank you. Okay, so we can move on to the next speaker, who is Timothy Foster. on mapping irrigating crop and dynamics with remote sensing for water policy design and assessment.
Which folder this is in?
Yeah, this one, I think. So first there. Okay, but you have to. Okay, and I think that the presentation mode. It does not.
Yep.
Yeah, it
Yeah,
will.
we're good. Right. Thanks, everyone. So I'm going to be talking about mapping irrigated cropland dynamics using remote sensing data for water policy designs. This is work that I've done together with two other people who previously were part of my research group. So Tom Higginbottom, who's now at Airbus UK, Roshan Adhikari, who's now at Nottingham Trent University in the UK. So we've had a couple of irrigation talks already, so I hopefully don't need to spend too long on motivating why we're looking at irrigation. So really, there's two reasons. So one, from the kind of the farmer's perspective, irrigation does two things. It helps you increase your average yield, but it also helps you reduce your variability in yields from one year to another. It's a buffer against rainfall variability and drought. A good example of that is the figure on the left-hand side, which is just the ratio of irrigated to dryland crop yields over time. And you can see that it's basically at least irrigated yields are at least double every year. But in some years, they're up to 10, 12 times what you get from rain-fed yields. So this is just an example pulled out for corn production in the Midwest in the US. I'm not actually going to talk about the US for the rest of this talk, but it's a good example because that's the kind of gains you get in an environment where rain-fed producers actually are already doing quite well. So even there, irrigation gives you a lot of benefits on top. Irrigated agriculture, though, is also important because it's a major driver of water scarcity and water pressures. It's the main user of water, and it's particularly the main consumptive user of water in most water-scarce regions around the world. So obviously, if irrigation is important, then we want to know where it's happening, how much water is being used. And there's a number of reasons why we might want data on irrigated land and water use. So one is that we might want to know it for regulatory purposes. So we might want to know where land is being irrigated, how much water is being used to check that that's consistent with water rights in a given location. We might want to use it because we might want to look for areas where land is not being irrigated, but we think it should be being irrigated. So to target interventions to support increased use or development of irrigation, or to support more sustainable use of water. And we also might want to use it to track how our policies and projects that we're implementing around water use in the agricultural sector are doing. Are they actually achieving the changes in water use and land use that we're actually expecting that they will? So the challenge that we often have, and I'm going to largely focus on irrigated areas in this talk, and I'll touch a little bit on kind of volumetric water use later on. Irrigated areas are very rarely actively monitored or recorded. If you try and go and collect information from secondary sources on irrigated areas for most areas around the world, even Europe, it's very, very hard to find. The maps and data sets that do exist, particularly at regional and global levels, are generally not very useful for practical policy decisions. And there's a few reasons for that. One is that they're often very low or coarse resolution. They might be 500 meters, kilometer scale. That's not capturing the dynamics of, say, smallholder farming environments. Where they do exist, they're also typically just single year snapshots, and they may be single year snapshots from 10, 20 years into the past. And in some cases, they're not actually maps of active irrigated areas. They're actually maps of areas that are equipped for irrigation and might be potentially irrigated. And the map on the left-hand side, which is a product that FAO produces on areas equipped for irrigation, is a good example of all of those. It's about, if I recall correctly, sort of a kilometer resolution or above. It's from data between 2000 and 2010. And it's primarily capturing the area that could potentially be irrigated in those locations, not the actual actively irrigated area. So the question that we've kind of been focusing on is kind of how can satellite data help to fill some of those gaps, and can it help to support decision-making around agricultural water management? I'm going to take you through two examples of work that we've done in this area. They're both sub-Saharan African focused, partially deliberate. It's an area that is very data scarce, an area where development of irrigation is also high on the policy agenda for achieving food security improvements, but also regional economic development. So the first thing that we wanted to look at is focusing on kind of big, large-scale irrigation schemes. So for those that don't know the context of irrigation development in Africa, the post-colonial period was very heavily characterized by the modes of irrigation development being building ginormous irrigation schemes, tens, sometimes even hundreds of thousands of hectares in consolidated lumps, typically funded by donor and development projects. One of the challenges of these projects is that the anecdotal evidence suggests that they haven't worked very well, but there's been pretty much no post-project monitoring and performance. There's usually an assessment done at the end of the project, maybe a year after construction finishes, but then the funders typically tend to walk away at that stage. And there's not active monitoring of irrigated areas by national agencies in these countries because there simply isn't the budgets and the capacity to do so. So what we wanted to look at is saying, well, if we look back at big, large-scale irrigation schemes in sub-Saharan Africa, how well have they actually done against their proposals? So what we did was we went into the World Bank, the African Development Bank's archives, went through all the planning documents. We were able for about 79 schemes to extract the proposals for how much irrigated land would be developed. And then we looked to do contemporary satellite-based estimates of actual areas under irrigation, which was kind of a three-stage process. So using very high-resolution imagery for developing a labeled training data set, and then training a random forest classifier using a suite of kind of Landsat-based spectral temporal metrics. I don't have time to go through in detail exactly which ones those were, but I'm happy to discuss with people later. And basically to produce annual probability maps for each pixel in each of the irrigated area schemes. We then, for the period 2014 to 2018, we then looked to say, okay, if a pixel was classified as being irrigated in at least 3 of the 5 years, we considered that to be an active irrigated pixel or portion of land in that area, with some rules around kind of minimum number of pixels in a surrounding connected area. The reason we picked 3 out of 5 is that there are obviously agricultural rotations, so land doesn't necessarily get irrigated or cultivated every single year. So it was a conservative rule to try and account for that. And then what we look to do is try and compare the two against one another. The colors, for some reason, have not shown up on this, so there should be nice colors on the little stacked bar chart here that denoted the different regions. The main kind of interesting takeaway from this is if you see the kind of the big black vertical line, that's the average rate of delivery. So on average of these 79 schemes in sub-Saharan Africa, they deliver around about 18% of the original proposed irrigated areas. And they're pretty consistently under-delivering. There's very few that get close to 100 and only a small number that get over 100. What we then looked at doing is we tried a number of things really to try and then unpack what exactly was going on. So what's driving this underperformance? I think this is perhaps an important kind of takeaway point on satellite imagery in this kind of context. It can tell you what's happening in terms of where the land's being irrigated or not, how intensely it may be being irrigated. Can't tell you why. Finding out why requires additional work, often work on the ground, to dig into the details and try and really understand the patterns that you're observing in terms of landscape dynamics. One of the things we found is that we looked to see if we thought when schemes were constructed might have an impact. It doesn't. Schemes that are constructed 50, 60 years ago are doing as badly as ones that were constructed 10, 20 years ago. We went for a variety of different things to try and explain what was going on. With the sample size, it was quite hard to, in the end, do this in a kind of a statistically quantitative sense. So we ended up having to revert to more of a qualitative storyline for how we approach this. But largely what we found is that large-scale irrigation schemes tend to fail and underperform for the same reason that most large-scale infrastructure projects fail and underperform. I don't know what countries various people are in the room, but probably everyone could name an example from their country of a big infrastructure project that had gone colossally over budget, colossally late, or maybe had just never been completed at all. And big irrigation schemes are really no different to that. They're often driven by political promises. So it's a great vote winner to say we're going to build a giant irrigation scheme that will supply thousands of people with water and revolutionize livelihoods. It's also kind of what the donors want to hear. They don't want to manage 500 small-scale irrigation projects. They'd much rather have one large consolidated investment. So to a certain extent, a lot of these proposals are kind of doomed from the start. They're proposing amounts that are really not feasible to achieve. There's also some subtleties that I'll come back to later about the types of crops that a lot of these schemes are focused around. They're pretty heavily focused around generation of subsistence crops. That does pose challenges for long-term sustainability and explains some of the patterns that we see. If you're proposing a very large irrigation scheme, to give you context, the cost of most of these schemes is about $20,000 per hectare in terms of how much they take to deliver. You have to produce a lot of rice out of each hectare of land to even make up that $20,000. And often there's a challenge around financial sustainability that stems from that creates this cycle of gradual decline in performance, then some more money gets chucked in, then further decline in performance, and eventually the scheme gradually runs down over time. A big challenge, though, is that when we presented a lot of this data, a lot of the donor agencies were really shocked. And part of the reason they were shocked is that they'd never actually monitored it because they didn't have a practical way to do so. And really, I think one of the takeaways for them was that satellite-based monitoring can, whilst it has uncertainties, be a tool to support increased transparency and learning about project outcomes over time so that you don't continue to repeat the same mistakes over and over again. So that was more of a kind of a contemporary example. The second example that I want to go through is looking at how we might do longer term backcasting and time series generation of irrigated area changes over time. Again, a sub-Saharan African example, so Senegal River Valley in West Africa, which is shown on the map. Similar approach here in that we used VHR imagery to develop, along with some existing land cover maps, to develop a set of labeled training pixels for cropland and non-irrigated and non-irrigated cropland, split over almost a 30-year period, and then use that to develop a random forest model that was a predictor of dry season irrigated areas that then could be applied backwards through time across each of the different years. And then one of the kind of the innovations in the method was using what's kind of known as a hidden Markov model to basically filter out some of the unrealistic transitions. You have variable levels of imagery from one year to another. Its distribution from within the year changes, and that can lead to kind of spurious classifications of land that's either irrigated that shouldn't be irrigated or not irrigated and should be irrigated. And you can use approaches like this to filter some of those out. So for example, if you have 10 years of no irrigation, 1 year of irrigation, 10 years of no irrigation, that's unlikely to be a realistic transition. That's a very kind of extreme example, but it gives you a context of kind of what that part of the model is doing. So these are kind of what we ended up with in terms of producers and users accuracy scores for the classifier for cropland and non-cropland. I'm not going to go into the detail here in great length, other than to say that two kind of things came out. One, we got pretty good accuracy across all years. If you're getting kind of land use classifications of 0.9 and above in terms of producer and user accuracy, that's actually pretty good. We have a number of years where we have gaps, and that's really highlighting that you have variability. The further you go backwards in time, the more variable the completeness of your Landsat archive is, and that also varies depending on what region of the world you're looking in. Landsat archive is not consistent everywhere across every time period. And that lack of images made it hard to produce classifications in some of the years that were further back. But one of the things we did find was that actually we were able to basically produce similar quality classifications all the way back into the late 80s as we are up to present. And that's partly a quirk of the system that we were studying, in that a lot of the agriculture back in the late 80s was large-scale sugar plantations with quite nicely defined boundaries, quite large plots of land that are easier to classify, whereas some of the smaller scale agriculture only came in more recent years, when we then had more imagery available to more reliably characterize. So what you're able to produce out of these methods is a variety of kind of different maps. This case, sort of, because it's Landsat, it's 30-meter resolution. You could obviously bring in Sentinel imagery for the more recent years to increase the resolution if you wanted to. This is an example showing kind of the first year that parcels of land were irrigated in the time series. So you can see that there's big areas in the sort of reddy, yellowy, orangey colors. Those are basically the big sugar plantations that were initiated in the 70s and 80s. And then there's quite a big gap between them that I'll show in a second. You can also produce maps of the frequency of which land is irrigated. Again, your sugar plantations area is pretty consistently irrigated throughout the time series, but there's lots of these other areas that are quite variable in how frequently they're irrigated. And some of that is rotation, but some of it is also linked to variations in the reliability of water supply in the dry season in this area. And then this is what it kind of looks like if we look at the kind of the annual area of irrigated land added. We've split this into Mauritania and Senegal because this is a basin that's shared between the two countries. You have quite a flat line until you get to about 2010 in terms of area being added each year. And that's despite the fact that the main water infrastructure in this basin, so there's two big dams, the Mantanali and the Diama Dam, that are kind of at both ends of the river sort of valley stretch that we studied. They were finished in the late 80s. There wasn't any major infrastructure constructed after that. Those schemes were proposing to add about 150 plus thousand hectares of irrigated land in that area. We reckon that in total up to present, they've got to about 50,000, and virtually all of that increase has happened post 2008 to 2010. And again, this is something that we can't quantitatively prove, but qualitatively and based on interviews with stakeholders in the region, we think this is really what drove all of this. 2008, 2009, there was a very large spike in global rice prices, and it led to a real kind of doubling down in several countries in West Africa and elsewhere in the world on rice self-sufficiency. And there was an enormous amount of money poured into this area to try and generate increased production. And we think that that's largely what drove this kind of big uptick in irrigated area growth in this region in this sort of post-2010 onwards period. So to kind of finish up with some sort of summary and recommendations. Sorry to you guys that have somewhat mixed those together into one slide. Hopefully this has shown how you can use satellite imagery to produce kind of spatiotemporal rich information about irrigated area maps with relatively light requirements in terms of kind of training data. In sub-Saharan Africa, what we found this is really valuable to do is to enhance learning about irrigation development trajectories, but also to start to track what the potential future impact of irrigation expansion might be on other downstream users. One of the things that we're looking to do going forward is to link the area mapping with satellite-based estimates of crop water use intensity to start thinking more about kind of volumetric water accounting, which is obviously the key kind of thing if we're talking about water allocation and scarcity. I've put a point there, though, that we do have to kind of have a degree of caution in that the levels of uncertainty on per area or per hectare irrigation water use from satellite data are a lot larger than the uncertainties around irrigated area or land use classifications. But there's enormous possibility for bringing those two together to support policy decisions. I think key challenges going forward, a lot of the examples I've shown you are quite relatively arid and semi-arid regions for the most part, with the exception of some of the earlier sites. This is a harder thing to do in humid areas, just because irrigation is then more supplemental and the difference in vegetation signature between irrigated and non-irrigated lands is smaller. But there are ways of getting around that, and particularly some of the newer satellite products may help with that. Again, disaggregation of crop types is a typical challenge of data availability. It's quite easy to do labeling of training data from things like VHR imagery if you're just looking at cropland, non-cropland, irrigated, non-irrigated, but getting down to crop types really requires ground reference data that isn't always available, albeit that data is getting better. And I highlighted some of the challenges, particularly if you're using Landsat as a means of going a long way back in time around the variable archives. Obviously, going forward, there's going to be enormous potential for putting, particularly in small scale environments, for enhancing the resolution of these maps, for integration of Landsat with Sentinel, but particularly some of the compositing approaches that have been started to be developed for land cover mapping, bringing together Sentinel-2 and Planet or other kind of microsatellite imagery. And then I guess there's a kind of a final point, partly because this is a kind of water and society event, and just to sort of throw this out here as a discussion point, I think one of the things when we start to develop these kinds of maps and data products that we need to think more about, and we don't tend to think that much about from the technical side of development, is what are some of the potential privacy, equity, social justice issues that might result from these data products being developed. And I think there's often an assumption that better data will lead to better outcomes and fairer outcomes. And to take the examples that I've covered, that's not necessarily always going to be the case. A lot of the agriculture that you're capturing in these environments tends to be informal, unregulated, and largely off the books. And governments are largely ignoring it because they don't have any data on it. Now, when they do have data on it, that doesn't necessarily mean that the outcome is going to be, yes, we're going to go and equip those farmers with lots of support and encourage them to help grow their activities. It might be that this is then a means of then blaming those small-scale farmers for issues of water scarcity downstream, which they may not be directly causing, or it may be a tool then to start regulating and controlling those activities that might be very important for local livelihoods and local economies. So I think thinking through some of the issues that result from the creation of new higher resolution data, particularly when they're linked to societal outcomes, is also very important. So thank you.
Thanks a lot, Timothy. Do we have some questions? On microphone.
Thanks, Timothy. Nice talk, really. Can you comment, please, a bit more on the challenges linked to humid areas? What do you mean, clouds or missing contrast?
Yeah, so clouds, obviously, cloud cover is going to be one of them because you may just have less imagery available. So that kind of spectral temporal metric approach, you're basically creating like composite indicators using multiple images over the growing season. Obviously, the less of those images you have, the more uncertainty you're likely to get in your classifier. But you've also got the challenge that just the more humid an area is, the less difference irrigation is making, and therefore there's if you look at kind of a vegetation signature over the season, the smaller the gap is, and probably then the more reliant you are on, say, high quality training data. But maybe in those kind of environments, you then have to start to use additional methods like looking to see if you can start to identify irrigation events happening alongside wherever the seasonal profile is distinct between the two.
So, temporally speaking, you surely mentioned about the crop rotation problem or not that you can have. What was your temporal range? Like, did you look at a yearly, within yearly? Because you showed the time series map, like changing from the late 80s, the 70s, 80s, up to 2000. So did you look at
Yeah, so we initially tried to develop separate maps for the rainy season and the dry season. The rainy season proved to be almost impossible because the Landsat archive is quite sparse for the majority of the time period. And in the rainy season, there were, up until kind of the early 2000s, there was basically no imagery available for pretty much any year. So we focused solely on the dry season, which in that region is kind of back end of sort of November, December through till about May, June time. So we were focusing solely on that seasonal period, but then producing kind of a single kind of classification for each season of was that land irrigated in that season.
So within the dry season, single crop is now there wasn't.
There's not usually double cropping within the dry season. It's usually a single crop. If there was double cropping, we'd effectively just be classifying it as irrigated, but not classifying that it was counted. We wouldn't sort of have irrigated ×2 there, and we didn't consider the rainy season because of imagery availability. But I think the rainy season for more recent years, where you've got combinations of Landsat 8, potentially Sentinel, then it might be possible to actually generate maps for the more recent years. But there's no way you could go back to the 80s with that. Yeah, and it would be a lot noisier in terms of separating the two out. Yeah.
So thank you very much. The next speaker is Chiara Corbari from Politecnico di Milano with a presentation with the title Multi-Scale Water Management and Drought Monitoring at the Morocco National Scale.
Okay, so thank you. And this presentation actually is part of the AfriSmart project, which is an ESA project for managing, to trying to describe and study the how we can reach and sustain a sustainable agriculture in Africa. In specific, we are concentrating in Morocco, and as you can see, Morocco in the last years experienced a lot of drought periods, and some of these droughts were very exceptional droughts. And also these, in general, North African is one of the areas which are also projected to be increase these kind of problems related to water availability. And of course, water availability is especially impacting agriculture in these areas. Then if you look in the left map, also you can see the water use efficiency. So it's a kind of indicators of the efficiency of really using then this water especially in agriculture. And you can see that it is used in a very bad way, so with a very low efficiency. So really there is the need to increase especially the efficiency in the management of the scarce water that they already have. So here the idea, the problem that what we are trying to address in here is to try to estimate but also forecast the water needs and the water availability at multiple spatial scales. So we are analyzing and try to understand how and at which intensity the drought occurs at the national scale, and try to see which are the impacts focusing on water availability, on stream flow at basin scale, and so try to understand, for example, how the different drought events could impact the reservoirs, so the storage, the water availability, that then is mostly used for drinking water, and only the remaining part could be used for agriculture. And of course, if there is no water for agriculture, in this area, there is a big problem of food security. As we were also discussing this morning in this morning section, there is the need to develop something that is really helpful, not something just out of research. And so we did a lot of interaction. We had a lot of interaction with the different users. And as the problem is not focused at a single small scale, also the different end users that with which we interact are mainly water operators, should be at different scales. So they should operate at the different scale because of course they operate looking at different problems also. So we are trying to interact from international scale, like from UNESCO or national scale at ministry level, down to the river basin authorities, down to the irrigation managers. And so this, we discuss with them the different approaches and needs that they could really be helpful for them, how they can match with our project objectives and outputs. And in the end, to try to provide them something which is also easy to use and easy to assess. So the focus of the case study is, okay, the Morocco area, and specifically, I will show you some examples from this basin in the northern part of Morocco, which is called the Morbia Basin, and the irrigated area of the Dukala area that is located downstream the Omrua river basin. And this basin has a lot of problems related to water scarcity. And in the last year, especially, there was a strong decrease in water availability. In fact, in the last 3 years, starting from 2020, the irrigation manager, the district stopped to provide water for irrigation. The only available water that was present in the bigger dam of Almasiria was used only for drinking water for the cities of Casablanca, mainly. So this is a real problem that they are already facing in these areas. So the how we are developing these activities, monitoring at different scales, the water availability, and of course try to forecast also this problem, because especially for the management of water resources at all the scales, what is important is that they especially asked us is, this is the situation, what will be the situation in the next months? So what is interesting for them, for water management, is to know for in the next 3 to 6 months, what will be the current situation in terms of water availability and the planned also water demand from the different possible users. So as we are working at different scale, we are also using different kind of data and modeling tools. You see here from the large scale national to the river basin scale, we are applying the VIC surface, land surface hydrological modeling that is connected with a rapid stream flow routing model that allows us to simulate the different storages, because in this area we have more than 10 dams, which are all interconnected and highly, of course, regulated, which are changing the stream flow. And from this big downstream Almasiria dam, they provide the water to the agricultural area, where we are instead using an hydrological model to simulate the crop water demand. And this is instead the final output, because the final tool that is provided to the users, because they want something which is easy to use and to understand. So maybe in respect to the scientific outputs that you can produce from the different models, then there is a need to simplify and to provide them something which is really useful and quickly understandable to them. So here is some results that we produced. This at the national scales based on the VIC model, which is a hydrological land surface model widely used. So we ran the model from the 1979 to 2022 with the collaboration with the Southampton University. And also we simulate the runoff in the different river catchments. And as you can see, there is a strong seasonal climatology with the rainy period, which is concentrated during the winter time and during autumn, and also like a small and oh, you don't see? Oh, okay. And also, which is concentrated mainly in the northern part and near the Atlas Mountain area. And of course, there is also some snow area here, which influences in a very small, which has a very small actually influence on then the river dynamics. What is interesting also to see is evapotranspiration, which actually is quite low, especially if we look at the entire Morocco area, but it also has like 2 peaks following the precipitation dynamic. And you can see also in the maps the climatology, but in general you can see that evapotranspiration generally, especially only except for the mountainous area, is quite low because the area is quite a dry area. And we did some initial comparison with other products, like for example for soil moisture, you can see for on the left hand side with ESA-CCI product, and on the right hand side for GLIM for all the years, and we can see a quite good behavior of both models. Then starting from this analysis of the water availability at the large scale, we move down to the analysis to the agricultural scale, where we use this FES EVB model, which is a water and energy balance model, which computes the, which solves the energy balance equation based on the land surface temperature, so that this land surface temperature is something which can be used to calibrate the model or for assimilating it into the energy balance equation, and it is then connected to the soil water balance equation related to soil moisture and irrigation effect. And the model can also simulate the crop growth, so that especially for the future forecasts, of course, the crop growth is conditioned by the water availability, but also like temperature stress effect. And so it is all connected inside one model. And one of the most important and difficult part in this quite semi-arid area is the simulation for irrigation. So we implemented the 2 irrigation scheme. One is the FAO approach, where it is a kind of optimal irrigation volume, which actually they are quite following because they do not have too much water to use. So the irrigation is triggered at a specific threshold, which is like the limit above, below which the plant is under stress. And it's not reproducing the real irrigation that is really happening, but it's an approach which is really useful for the planning for future projection. Then we implemented the second approach, which is based on the assimilation of land surface temperature, based on the downscale and Sentinel-3 land surface temperature data on the Sentinel-2 data, to have at 30 meters spatial resolution a land surface temperature. This land surface temperature is something that provides you information on where irrigation is really happening. And potentially, if this land surface temperature is used to compute evapotranspiration, it's also providing you an instantaneous estimate of the evapotranspiration, which of course, will be different if the field is irrigated or not. And this, if it is compared with the simulation of a land surface model, which do not know when and where irrigation is happening, you can, assimilating this information, you can inform also the land surface model about what's really happening in the field. Of course, you can have, I will show you how it's working. And then the last part, of course, you should think about the efficiency, because they are mainly using flood irrigation techniques. But in Morocco, there is a very strong financing by the ministry, the government, to invest in using drip irrigation systems. So in the last year, they are changing quite a lot, also because they do not have anymore enough water. So this is also a big investment. So we started, and I will show you some results of the calibration. Then we monitor what's really happening, try to assimilate the land surface temperature, as I told you, and try to see if the FAO approach, the FAO approach, is comparable. Also trying to compare with some observed data that we had. And then I will show you finally some results of the forecasted approach. What is important also for modeling, as also Timothy was saying, is to try to understand which are the real cultivated area. So we first try to analyze, starting from the vegetation fractional cover from Sentinel-2, so using the time series over for different years. You see here some example, and the standard deviation over all the season, because here they also use also like 2 crops during one year. And as you can see, starting from 2020, the cultivated area started to decrease, and especially in the last year, in 2022, the fact that they stopped providing irrigation, you can really start to see that they sensibly decrease the cultivated area. Instead, already in 2020 and 2021, they have already stopped providing the irrigation, but they also have a lot of private pumpings wells, so that they also pump a lot of water. But 2022 was also very dry, so the combination of the two. And the same, we use then the land surface temperature. Actually, I'm not going into the details of it. We use the data from the Landsat, but Landsat data 8 and 9 are available every 16 days, plus clouds. So we downscale the Sentinel-3 data, land surface temperature, based on this algorithm, based on vegetation, on DVI information at high spatial resolution. And this is very important, because we first use this kind of information for validating the model, because the land surface temperature is an output of the model. And in that way, you can compute and compare the output of the model. You see 2 images as example, one in the summer, one in the winter. At each single pixel, you can compare the capability of the model, and then you see the temporal dynamics. So potentially in each single pixel, you can calibrate the modeling parameters and the scheme. And we also did some intercomparison, for example, with some evapotranspiration products. And what you can see is on the left, you have the FESVB approach with the FAO for irrigation, and on the right with the assimilation of the LST. And we compare it with the MODIS data, which are from at 500 meters. Sorry, it is an average of every 8 days. Instead, the vapor is at higher resolution, but it's a value accumulated over 10 days. So in the end, we compare at monthly scale, even though we are simulating hourly. And you can see and you can feel some differences. Oh, no, there is, okay. And you see that there is quite a good agreement, especially with the MODIS product. And in general, also like the Pearson coefficient is quite high. There are some differences, especially in the summer months. And in the summer months, these areas are very dry, but are cultivated. But the problem is that the fields are very small and are like locally irrigated, but the surrounded areas are really dry. So also from satellite information at 1 kilometer of spatial resolution is not easy to see these differences and to detect these small plots. And this is especially visible if we take these the data from of soil moisture. It is the SMAP Sentinel-1 at 1 kilometer, downscale at 1 kilometer. And in fact, you can especially see these differences in this period, starting from June to September. And you really feel these differences that in this specific very quite arid, semi-arid area where only small fields are cultivated, it's really difficult to detect. Instead, for example, this is the same behavior, but for a pixel, and of the SMAP Sentinel-1 soil moisture. And inside, looking at the Sentinel-2, if you look at the green line, there is one pixel which is fully cultivated and another field which is bare soil, which is not cultivated. But the number of pixels in general are more bare soil than cultivated. So it's if you look at larger scale, it becomes difficult. I think that the time is quite running, but I will go quickly to the last 3 slides. Here you can see from then, of course, for this is a year, you can see the agricultural water cycle components, because what the last step was to compute the crop irrigation demand. So to try to understand what is the need, considering also irrigation efficiency, because from the crop irrigation water use to the irrigation water demand, then there could be a big differences, to try to understand how it can change during the year and across the different years. And this is like a summary, but these are the single maps. But then again, as I was saying in the beginning, the end user, the water manager, are not interested in this kind of so high resolution maps, especially at the district level, not the single farmer, okay, but the district authorities. They were more interested to have, they were more interested to have something aggregated in sub-districts, because they are providing the water according to the demand of all the farmers. Usually this is done by phone, asking the single group of farmers that are inside the different sub-districts. And these are, for example, the results. I'm sorry for the yellow line. On the left, you have observed volumes provided by the irrigation districts, the volumes using the 2 irrigation approaches. You see that there are some differences, some agreements, but the problem is that the observed volumes are not the real irrigation volumes that they provided, because we know they told us that actually they're using a lot of water from groundwater, especially during the last years when they provided 0 water from the irrigation authority, and instead the areas were irrigated because this was visible. There were a lot of vegetated areas with a very high evapotranspiration, looking only at remote sensing data. So to conclude, these are the same thing summarized over the different years. And okay, if you look only at, I will finish with these slides. If you look only at the plot, you see that with the blue and orange, you have the results from the two approaches, and in yellow the observed data. You see that more or less when the water was provided, the results are quite similar. Actually, we were expecting to find something more, especially with the assimilation of land surface temperature, but also if you look at the number of images, probably we are missing for sure some of the irrigation events. So in the beginning, we started to also try to analyze some soil moisture data, why we don't assimilate them, but then in the end, the results were worse because the images were even less. And then also, as I show you, we were not able really to see the small fields which were irrigated. So in the end, we even get worse results. So probably in an integrated approach, trying to use and merge different kind of remote sensing data could help to increase the information on irrigation and also in the spatial resolution. So thank you.
Thank you, Chiara. Maybe we have time for a quick question.
It's too long, sorry.
I'm very surprising you're able to make forecasts for discharge for several months. It's very unusual,
Yes.
because the meteorological product for such, sometimes it's just, probably it will be more than the average, but they don't want to give more precise figures. So perhaps you have access to more precise figures for forecast.
What you mean by providing like short-term forecasts?
No, you speak about 3 months or?
Yeah, because they are interested in knowing this, especially for water availability, not real discharge, but water availability. Of course, there is uncertainty, but this is what they are mainly interested in. And we are using, I didn't show this, I didn't have time. We use the SMWF weather forecast, and this is an example for evapotranspiration. And in blue, you see the forecasted 6 months.
Okay, so you have the data from the
different- Yes.
ESA-ESRIN for 6
Yes.
months. Okay.
Yeah, but is the meteorological data, then it is used as input into the model.
Yes, of course.
Yes.
Thank you. So we can move to the next speaker. Okay, Esther Greenwood from ADH, mapping safe drinking water in low and middle income countries using Earth observation data.
Hello, everyone. Thank you very much for sticking around until the end. I'm going to try and keep this presentation fairly high level, so if you have any questions, then feel free to approach me later on. So the work I'm presenting is part of my PhD, which I'm doing at EAVAG and ETH Zurich, and it's a collaboration between the ETH Zurich Crowther Lab and EAVAG and the Joint Monitoring Program for Water Sanitation and Hygiene, which is a WHO UNICEF program. So I'm sure most of you or all of you are familiar with the Sustainable Development Goals. And today I'm going to focus on Sustainable Development Goal 6 and Target 6.1. And when it comes to Sustainable Development Goal 6, we are faced with the challenge of major data gaps. So Target 6.1 is about safe drinking water. And so for safe drinking water and access to safe drinking water is not only a human right, but it's also vital for human health. And there are different aspects to be considered when we speak about drinking water. So even though it's important that we have fresh water available, it's not ensured that people are using a water source which is free from contamination and that they have it in the house. So the indicator to monitor target 6.1 is the proportion of people in a population using a drinking water source which is improved, so it's protected from exterior contamination, which is also has been tested to be free from contamination we use. In this case, we're focused on fecal contamination using E. coli as an indicator, and this is tested at the point of collection. So this could be a tap, this could be a well, depending on the drinking water source used. And it's also considered that the water source is on premises, so it should be accessible and also available when needed, so people should not be experiencing insufficiency. So I'm going to be referring to safely managed drinking water use throughout the talk, and I'm basically then speaking about drinking water which fulfills all this criteria. And I'm also going to be speaking about the subcomponents of safely managed drinking water, and here I'm referring to water source type, so if it's improved, not improved, drinking water contamination, so it's free of fecal contamination, accessibility, which means that it's on premises, and availability, which means that people haven't experienced water insufficiency in the last 2 weeks. So if we look at the most recent report on which has been released by the Joint Monitoring Programme, which is the custodian agency responsible for monitoring progress towards this SDG, we see that we still lack data at a national scale for approximately half of the global population. And so to collect data on this target is very time and resource consuming because it involves people going to drinking water points, collecting samples, which need to be incubated for 24 hours, and then also asking a lot of survey questions. Yeah, so this is a major challenge, and this is what we're focused on. We're not the only ones when it comes to lack of data on the SDG target. This is just an overview, so this is really a big challenge to fill these data gaps. And so what we've been doing in this project is we've been seeing if we can address these data gaps on this sustainable development target using Earth observation products and combining this with household survey data, which has already been collected and exists. So the data which was used for the models which were developed were collected from 27 different countries. The original data set was around 63,000 households which were surveyed, but this was drastically reduced because we didn't have the exact locations of the household. This is something which only in the past year has started to be released by this survey program. So at this point, I will show how we then aggregate the data. But at this point, our data set only had 319 observations, which were at subnational district levels. And this is the multiple indicator cluster survey program, which was used. So if we look at the modeling pipeline, again, we have the safely managed drinking water services, which was then combined with Earth observation features, which were sampled and averaged at global administrative district levels, mostly 1, but also sometimes 2 and 3, depending on the highest resolution of information which was available about the location in the survey data. And we then developed random forest models combining both the survey data and the Earth observation data. And this we did for the outcome safely managed drinking water services, but also for the subcomponents, so developing further models which were for drinking water contamination, accessibility, availability, and the water source type. I'm not going to go too much into our validations, but we did a leave one out, so leave one country out cross-validation, where we trained the model on 26 countries and then validated on 1 country which wasn't included and rotated, and then used those to compute metrics. We also now are putting together a test set. So we have 5 countries which were not included to develop this model, and there are more being released with which we want to then validate the models. And another thing we did was to compare reported data from countries which collected their own or produced their own estimates with different methods and kind of compare how our estimates are towards those. So this is to understand how the outcome variable is. So we have different households in a region and we don't know the exact location. So we just calculate the proportion of those households using safely managed drinking water at the subnational district level. And then combine that with the averages of the Earth observation data. This is an overview of the final feature set. I'm not going to go too much into detail here due to time, but we started off with a feature set of around, or of 121 different features which were used mainly in ecological modeling, and we selected them based on their relevance and reduced then also by looking at model performance with different subsets of those features. So our outputs are our maps. On the one hand, we map the outcome, which is safely managed drinking water service use. So here we have the proportions. So the light colors are where people have very low coverage rates of safely managed drinking water services. You'll see that our estimates are very low. Already in our training set, we had a large proportion, or the majority of countries, the coverage was under 50%, and the highest at a national level was just about 70% coverage. So looking at low middle income countries, we expect generally low coverage rates of safely managed drinking water services. We then also model this, we also map this looking at the number of people. So this is mainly driven by population size, but it's the same outcome. So you have the darker areas being ones where there are not so many people, and then the light ones being ones where there are a lot of people who don't use safely managed drinking water services. Something we also look at are then how the different features contributed to our model, so the prediction of safely managed drinking water services. Here we grouped the features. So based on our classification or our definition of human features, those were the ones which contributed the largest, the most to the safely managed drinking water service outcome, then followed by climate variables. We also looked at this for the subcomponents and found that for the subcomponents which had to do with infrastructure, so the type of water source which was used, or if it was accessible or not. For these ones, the human factors were also the most important. For E. coli contamination, the climate ones played a larger role. And then for availability, the biogeographic ones played the largest role. This is just, so we can see the 20 most important features. I'll just highlight an example for the human feature. So the most important one was the urban built-up land cover. Here, so the observations, which are dark, those resemble low values. So in this case, it's basically low urban land coverage. And then the light values are higher. So for urban built-up land cover, we have lower land cover of urban built-up contributing to lower estimates of safe drinking water use. And this is quite intuitive, as in rural areas, generally lower coverage rates are observed compared to in urban areas. And then we have other ones. So for example, the annual mean temperature would be a climate would be a climate feature with a fairly clear trend. So here we also have so we would have high annual mean temperature contributing to lower estimates of safe drinking water. And here I just want to highlight that we cannot say that these are causal relationships. We think that a lot of these indicators are geographic indicators. But yeah, it's interesting to look, and we were interested in discussing what the connections could be. So now I come to the subcomponents. So this is the first subcomponent, which was the type of water source. Here you see the proportion of people using an improved drinking water source. And this is quite different to the image where we looked at safely managed. So an improved drinking water source could be piped water. It could be a protected well. It's basically any drinking water source which has been constructed in a way that it's protected from exterior contamination. And what the contrast tells us is that even though people are using piped water in many countries or other drinking water sources which are protected, they are still affected by either contamination, accessibility, or availability lacking. And so that's why we also map, based on the other models we have, where in the world which of these subcomponents is the limiting factor. So the countries or areas which are red, they would be mainly affected or predominantly affected by drinking water contamination, whereas those which are green would be mostly affected by people not having drinking water in their house or on plot. Someone, for example, in an area which is green might have piped water in their neighbor's house, which they might be using. So, but based on the criteria, they don't have safely managed drinking water in their own house. And availability is also, so we don't actually see a lot of areas which are predominantly affected by availability. And the outcome here is the experience of water insufficiency. So someone who's living in a house with intermittent water supply, who stores the water, would not necessarily be affected by water availability because they would have enough water based on their household practices. So this is a little bit, this was also the most difficult component to capture with the Earth observation data. So summarizing, we can see that we're very far, and this also aligns with other reports, we're very far away from reaching universal access to safely managed drinking water. And we're hopeful that Earth observation derived products in combination with household survey data can help us fill some of these gaps, and may also be, we believe these methods may also be applicable to other indicators which are predominantly collected with household survey data. These models are in no way perfect, and we're continuing to improve them. So one thing we're looking currently at is improving the spatial resolution. So there have been surveys now released with georeference coordinates, and we are now matching those to build higher resolution models. Another thing we'd like to look at is the temporal resolution. So safe drinking water is not a static, it's not the same every day. A lot of households, you would go there and measure drinking water contamination on one day, and the next day they might be free of fecal contamination. So to be able to capture these temporal dynamics, we're now also matching the Earth observation data, especially like the climate data, with the time of sampling, and trying to get that also higher resolution predictions and look at trends. And then I would like to thank once again all the collaborators and people who are involved in this project so far, and funding from the Swiss National Science Foundation. Thank you very much for listening.
Thanks. Do we have questions?
Previous.
You have a question, Jerome? Okay. No. Could maybe ask to have better details on which AO data did you use or are you planning to use to better describe this?
Yeah. So this, I must say, has been for me personally quite difficult to select because there's such a wide range of products. And so for the higher resolution data, I was basically looking on Google Earth Engine what was available. So I'm sure there's better products available, but the criteria which I used there was basically to have a high temporal resolution and spatial resolution. And so for land cover now, I was looking at dynamic world products, which I heard different opinions on about how accurate those are. For the other modeling, which was at a global scale, we used consensus land cover. And then for other, I mean, there was a broad range of features which were used, and those most of them came from different sources. But this is something which I'm very open to review with people with more expertise.
Thank you. Other comments? Yes, please. At the microphone, please.
One more like a suggestion. Thank you for the presentation. When you showed us all the figure with a bunch of this one, so it would be interesting to see. Have you ever looked into structural equation modeling?
Mm.
So you can kind of model the covariance, covariation, codependence of some features. So for example, we might say urban building, urban built up can affect the water availability through one of these variables as a proxy, right? So you can have a direct effect, you can have indirect effect through other variables. So that would be interesting to see. Because there are many variables considered.
Yeah.
Just
Yes. Yeah. And also, so some of them are correlated and clustered together. So depending how many clusters you have. So I also observed, like when you remove, for example, if you remove urban built up, then population density comes to the top. So I think a lot of these may be describing similar patterns in the data. Yeah. Okay, thank you. I'll look at that. Yeah.
Thanks for the presentation. It's just a comment. I had an impression that the maps are a little bit homogeneous. I don't know if you have the same impression. Some of the maps, and one question is if you check these results with information from the countries. You showed one of the maps. I'm from Brazil, and for me, it's a surprise. This is the numbers in the map, because I don't know if the same concept of potable water and safe water, but around 80% of the Brazilian population receive potable water. So in terms of quality, around 80% receive. But sometimes the problem is the amount, the availability, the water availability. But in terms of quality, around 80% receive water in the house.
Thank you very much for that comment. We did compare, and actually Brazil, the predictions and the reported estimates are, I think, one of the most different. So I also saw these numbers, and I think now they also have a new survey which has come out, so they're also updated estimates. I think one limitation in for this model is the training data that was. So if we look at all lower middle income countries and we map all lower middle income countries, the largest proportion from low, lower middle, and upper middle is actually upper middle. but the data which was available on safely managed drinking water services is largely from low income and lower middle income. So I think that we are compared to other results, which are sometimes Brazil is one of the few countries, the upper middle income countries, which has this data at a national scale. If we look, yeah. So Brazil is really one of these countries which collects this data. But in our training set, yeah, I think may be biased towards lower countries because those are the ones which collect this data also with these survey programs. So I think there are not so many countries like Brazil which collect low and middle income countries which collect their own data. So including, for example, data from Brazil to the training and maybe some few others which might have this data available, I think could really improve predictions for upper middle income countries. Yeah.
Okay, so thank you all for the discussion, the discussion that we did after each presentation. And I think if there are any other comments or general comments or general questions, otherwise I think we can close the session and see. Okay. Yeah.
No, I just want to make a generic statement that I think safe water drinking is absolutely very important, and I wish you can help us draft something bold and serious of the recommendations of what agency can do, and a little bit more than the last slide that mentions that we're not nearly there, and EO can help go develop that into some details. If there's some specific data that needs to be better served for a better use in this direction, because I think it's we've talked a lot about lack of water or too much water, and when we have too much water, of course, it's dirty water. But I think safe drinking water is a topic that should take more space in such a workshop. So looking forward to write something from your presentation into the report. Send the chair some requirements and recommendations. Yeah. So if you guys are going to close this session, then I'll take just 10 seconds more to thank all the work that was done by the co-chairs, because it's not easy to shape the future. And then the 42 co-chairs of this workshop have to also boil this down to something which is readable. So thank you very much.
So we can close the session, I think. We will see for dinner, right, later. Right. Thank you.
Anticipated that we have a group picture just now at 18:10, but I think a lot of people ditched a bit early, and so it won't work. But let's pass the message around you that tomorrow at the beginning of the lunch break in the stairs, you stick around in the stairs. We wanted the drone to take off and take a picture of the whole group, but the batteries are not allowed in the airplane. But if you want to be on the pictures, try to stick around just at the lunch break tomorrow.
Stiamo per iniziare.